Okay, good morning, everyone. Thank you all for coming here in person. Uh, there's a whole bunch of folks virtually connected, and welcome to them too. Good morning. It's a great pleasure to have our first event for the 75th anniversary, and it's also a great pleasure to have one of our Dean's Advisory Council members, co-chair of the 75th, co-chair of the Dean's Advisory Council, participating in organizing the 75th anniversary celebrations for the College of Engineering, Mr. Alan Sirkin, and he is also a big benefactor of the college. And we've invited him to welcome the group and make a few remarks. After he's done, we'll continue with the program. Alan.
Good morning. As you said, my name is Alan Sirkin. Welcome. This is certainly an exciting event. First one, I understand. So I'd just like to say how much I believe research is important. I remember when I was a student here at UM, the best part of studying engineering was the laboratories and learning about new things and how to create things. And that's always been with me. So as far as these days, I've been fortunate enough to donate money that has gone to research. We contributed for 2 testing machines that are used in the structural engineering laboratory. And the one that I'm most proud of is we contributed to a sustainable boat dock that is made without any iron reinforcing bars, but is all reinforcing that is natural. And it's strong and it should last for 100 years. The current problem is that docks and seawalls that are made with iron rust over 20 years and have to be replaced. So this is a whole new procedure. And the good part is some of the graduate students that were working with us on the dock have now gone on to start their own company, and they're doing green seawalls and green docks. So that's my story, and I'm sure you're going to hear a lot of interesting research projects today. So welcome.
Thanks, Alan. I must also say that recently, if you walk by the second floor of MacArthur, you'll see a plaque recognizing his contribution for the Dean Suite, and that is discretionary support. So thank you, Alan, very much. I must also recognize Alicia Sirkin. Thank you for coming. And both Alan and Alicia have been supporters of the College of Engineering. There are many of you virtually connected, so welcome. I just want to make a few remarks. The College of Engineering is going through several transformations, again, thanks to support of our alumni and other individuals. We have identified a set of strategic initiatives, and it's sort of answering the big challenging questions, working together across the departments in areas such as health engineering, advanced materials, sustainability and resilience, space sciences and engineering, data sciences and engineering, and then also energy and environment. And then we have several cross-cutting initiatives focused around innovation and entrepreneurship and international alliance, and then also excellence in teaching and learning. So all of this really reflects and is supported by the college research that many of our students, faculty are working on together. All students, undergraduates, masters, doctoral students, and also research scholars, and of course faculty. So it's great to have this. Dr. Helena Solo Gabriel, who's our Associate Dean for Research, has really put this fabulous event together. And I just want to make a closing comment before she comes on and tells you all about the exciting events for the day. We are going to have one event every month, and this is more targeted to our alumni and well-wishers who are probably listening remotely. Please tune in. Every month there is going to be an event to celebrate our 75th anniversary. So we look forward to even seeing you in person at some of these events. Thank you all for connecting, and I'll just turn over to Dr. Helena Solo-Gabriel. Thanks.
Thank you so much, and thank you, Alan, Alicia, and Pratim, for this opportunity. And I'd like to go over the agenda for the day. And the agenda is as follows. We have split this event into 2 rooms. One will be here in the auditorium. All the speaker sessions will be here in a hybrid format, both in person and virtually. And then we have a poster session that will happen during lunchtime over in the pavilion. The first session is really this introductory session. Again, thank you again, Alan, for the introduction, Pratim. And then after I go over the agenda, Renee will describe the poster judging. But after our introductory session, we then have the first speaker session on engineering cures for cancer. We'll have a break, and then the second speaker session on advanced materials for manufacturing. We then go to the poster session in the other venue in the pavilion. And then after that, we will come back here for the last session on advanced materials in healthcare. We'll have a closing session focused on the poster award session. Okay, so the first session is chaired by Dr. Ashutosh Agarwal and Stephen Neimer. The second session is chaired by Emra Selick, James Coakley, Luis Ruiz Pestana, and Dr. Giacomo Ho. And then we have our poster session. We separated the poster session into 5 categories. We have an undergraduate session, and then 4 additional sessions that will be presented by graduate students. So the 4 sessions include energy, environment, and manufacturing, healthcare and biomedical, materials, and machine learning and computer science. And then after the poster session, we have the session chaired by Dr. Kizraev and Dr. Mons. At the end, we will have our poster awards. The president of the Graduate Engineering Student Council, Mohammed Gaishan, and Renee Evans will be presenting the poster awards. And I'd like to ask that all poster presenters and everyone here to come back at 2:15 so we can enjoy and celebrate the announcement of the poster awards. At this point, I'd like to hand it over to Renee, who will describe the poster judging.
Okay, good morning, everyone. So for the poster judging, as was mentioned in a previous slide, the posters are divided up into 5 categories. And for each category, the criteria that you should be looking for when judging the posters include quality of content, clarity of content, quality of content, results and conclusions, significance of study, graphs and visuals, informative, oral skills, and proficient expertise. So each criteria will use a 5-point scale, and our judging is online. It's an online form. We do have paper forms available if you have any issues with the online form. But when you access the online form, it should look something like this. The posters have been coded according to a specific ID along with the presenter name. And then we have the judging criteria and then the scale from poor to excellent there for you to make your selections. For some categories, for some criteria, you may have to scroll over to make sure that you put in all the entries for each poster. Accessing the form, that is the link to access. I have a link as well as a QR code. For the For the people who will be judging the posters, I do have handouts that I can give to you where you would have the link and the QR code. And if you have any questions or issues, I will be available over in the judging section if you run into any issues or have any questions. All right, I'll pass it back over to you, Dr. Soho.
Okay, at this point, we'd like to begin with engineering cures for cancer. Dr. Agarwal?
So this is your inbox. Yeah, Stephen is online. Dr. Naimur, if you could give us an audio check, just so we know we can hear you. Virginia, is he speaking? We want to be able to hear him. I'm sorry? Well, that's not. Okay. So. Yeah, I know. We're just going to have to jerry rig something. Can you give us a sound check again, Dr. Naimur?
Yes. Testing 1, 2, 3.
Right.
Okay, if people can hear me, I'll just...
Is this microphone active? I'm just going to place a microphone on this computer, Dr. Naimur. Can you activate this?
Tell me when to go.
Okay, I will. Okay. Stop sharing. I'm going to place a microphone. Just give us 1 second, Dr. Naimur. It's coming through this computer. I just need this. Yeah, but it's not loud enough. Just give us 1 second, Dr. Naimur. Zoom on it. It's not this weak. We can hear him on this computer, but not in the room. Sorry? Oh, it wasn't.
Let me change it.
Can you, again, sorry, Dr. Naimur, last sound check. Can you give us a sound check again?
Hello?
I think the people on Zoom can hear him, okay? So let's welcome him on Zoom and... So maybe, Dr. Neimer, what we can do is, if you can hear us, sort of have you, wow. Share screen again, yeah? I think,
Wesley, quita el audio, que está controlando. Quita el control del audio, por favor.
my suggestion is if people on Zoom can hear him, let's just go and have people to Zoom.
Hello, hello. Hello.
Dr. Neimer, do you want to just go ahead and present?
Hi, Steve, can you just speak? We'll use the phone, okay? Okay, so it's a great pleasure to have Dr. Stephen Neimer with us. You know that we ran into some technical difficulties here. He's on the medical school campus. Dr. Neimer is the director of the Sylvester Comprehensive Cancer Center. It's been a great pleasure for our entire College of Engineering to be working with his group and the faculty researchers and other staff at the Cancer Center. As you know, cancer remains a very challenging issue, both in its detection, diagnosis, and treatment. And engineers being problem solvers, you know, we want to take on this challenge, work with our colleagues in the medical sciences, and begin to make transformational changes in these areas. So there is an initiative that has been launched now, and Dr. Neimer is really working very closely with us. So I'll request him to make a few remarks.
Thank you, team. Can you hear me?
Yes, we can.
So, first of all, I'm absolutely thrilled to be working together. Yeah, I'm not sure if, I guess people can hear on Zoom. But let me just see what I can do. In terms of the technical. Yeah, hold on one second. Maybe I can.
Zoom?
Okay, does this work now? Can everybody hear me, or is there an echo?
No, it's fine here. In the room, it's okay. Please proceed.
Okay.
And we can hear on Zoom too.
Great. So I'm absolutely thrilled that the Cancer Center can partner with the College of Engineering, with Dean Biswas, and our goal in this year in particular is to develop as many collaborations as we can that can yield meaningful and important research projects. It's nice to see Helena. I will say that Helena got a very large grant on wastewater and COVID, and George Grills, one of the leaders in the Cancer Center who runs our shared resources, I think was very important, and it's just one example of how we can work together. The dean attended our retreat in November, as did a couple of the members of the College of Engineering, and it's really fundamental that we learn to understand what each other's doing, forge friendships and relationships and collaborations so we can move things forward. The dean and I, at least for me, I got my first trademark. The dean and I have trademarked Engineering Cancer Cures, the name of our joint initiative, and we expect to fund projects, to do some co-recruiting. We have provided some biosafety hoods and other things on the Coral Gables campus to both show our intention to work together and to put resources into the pot, and also to find ways of getting additional funding, philanthropy, federal funds, state funds. I would love to be there today. One, I was up in Tallahassee yesterday trying to raise some money from the state government, and hopefully was successful in that. And then if you go back, I think Ashutosh put this slide in. There's our Dolphins Challenge Cancer event is tomorrow. We expect to raise perhaps up to $7 million from the event. That's me there, but there's going to be 440 people riding 100 miles on a bike. I'll be one of them. At 6 a.m. We leave at 6 a.m. And so it's an example of how the community helps us, and we then can help the community by doing impactful research. If you can go 2 slides more, we focused on 3 areas for initial research, sort of intelligent materials, cancer tissue engineering, and artificial intelligence and machine learning. Shanta Dar and Ashutosh Agarwal have worked together both for evaluating proposals for the initiative and also helping us organize some of the many meetings that we've had. College of Engineering faculty have come to Sylvester, and if we go back 1 slide, you can see we went and visited on the lower left there is our visit to the College of Engineering. We got to see your 3D printer and had a great time. So I'm going to turn it over to Ashutosh because 1, he's physically there, and 2, he's the engineer. And so, please think, creatively. We think there's tremendous opportunities for our ideas to move forward, both in the academic world and in the business world with startups and other things. And if we think of this as a baseball game, then we're just at the beginning of the first inning. So there's lots of fun things to do together. Thank you, Pratim, for inviting me to help kick off this year's celebration, and congratulations to everybody involved in the engineering college who have brought us to the 75th anniversary today. So the best is yet to come, as I like to say. Thank you.
Thanks, Stephen. Thanks.
Thank you, Dr. Neimer. So Dr. Neimer already introduced the 3 areas of focus that we started with, and these were based on initial surveys of the competencies that exist within the college and the needs that might exist at the Sylvester Cancer Center. So Shanta, don't go away. So I want to introduce also Shanta, my partner in crime. So she's the representative from Sylvester, and Dr. Dhar has been a great team player in corralling leadership behind these 3 subgroups, and the subgroups are targeting intelligent materials, cell and tissue engineering, and AI, machine learning, deep learning-based analytics, and image development software. So if you have any questions or complaints, Shanta's here. It's been great working with not just Shanta, but also all of these really busy investigators at Sylvester. From engineering, Sakrat represents a Sakrat and Shanta co-leading the efforts on intelligent materials. Josh, who's an amazing pancreatic surgeon, he and I are leading the cancer, and he's so generous with his time. It's unbelievable how committed Sylvester investigators have been to this effort. And in artificial intelligence, deep learning, Stephen Schurer and Ola, I think as well, has been co-leading the AI effort along with Mohammed, who's here. Under each of these chairs, co-chair structure, there are friends and family within each of these 3 subgroups who attend our monthly, sometimes bi-monthly meetings to keep up the momentum. And one of the things we did to initiate this was to have an RFA on the street. And many of you might know about the RFA. We actually ended up receiving 11 applications. It's for a fairly modest-sized College of Engineering, 11 applications that represented 14 engineering PIs and 19 Sylvester PIs for a very short time frame of an RFA. Was very, very impressive. We sent those proposals out for external reviews, and we invited only non-UM people for a completely unbiased review. We've received those reviews back, and we're close to forming opinions and decisions on funding. So, task number one within this initiative we've already achieved. Over time, you will see a cluster of faculty recruitment, hopefully, within the new Department of ChemE, perhaps biomedical engineering, which might have a cancer focus. Dr. Naimer already alluded to point number 3, which was establishing core facilities. Some of that has happened in engineering already. And then over time, we want to develop, for example, the T32 grants that might focus on cancer engineering. And eventually, this will tie into the cross-cutting initiative of entrepreneurship and technology development. So the idea is that over time at UM, at College of Engineering and at Sylvester, we would establish by the end of 5th year a robust cancer. All good College of Engineering have a nice cluster of people working on cancer engineering, and all good cancer centers have good partnerships with engineers. And that just has to happen here, and that's the whole focus. And then you can read through our laundry list of quantitative milestones we want to hit at the end of 5 years to show that we're doing something good. So with that, I think we'll open it up to questions. I want to thank Dr. Naimer and Shanta, who is actually here in person. And the floor is open for discussion. Thank you. Link for Zoom. A recording. Okay. Well, we just finished the presentation, and the floor is open for any discussion. For folks on Zoom, if you type it in, we can monitor the chat. If not, we can give you your 15 minutes back. Good? Thank you. We were out of here. It's the language. It's always the language. It's like you need a Condu. Yeah, so this actually came up a lot when I was trying to get people to talk to each other. You always perhaps sometimes need an interlocutor between, these two very different universes of, a deep mechanistic cancer researcher and a tool builder in College of Engineering. And I would argue that, I'm biased, but biomedical engineering faculty tend to do well in that setting where they understand both the languages, right? So perhaps you just need that interlocutor or an RFA like this to force people in a room and get working. Because I'm convinced, and I've made a career out of this, that the tools we build in engineering, which might seem trivial to us, are so useful for serving as test beds for people who do basic science. And we just don't know what the needs are from the other side. Well, I don't know if the other side can hear us right now. Sorry?
No, definitely. I think Otherside feels the need for engineers and create a lot of things. I'll give an example. Recently one of our colleagues who was telling, she wanted to treat peripheral neuropathy in her patients. And she started thinking whether she can make gloves containing hydrogel, which can lower some of the chemotherapeutic infusion to the cells and lower the peripheral neuropathy. So I think there is a lot of need, and even clinicians understand that. Again, as Ashu mentioned, is the language barrier, and I think one of our first slide when we started this initiative the first line was, we want to break that language barrier.
Yeah. One of the things the 3 subgroups are doing in that area is we're organizing now these brainstorming sessions where the PIs are allowed to present just one slide, but then there's a 60-minute discussion after that. And the slide is a need slide, right? What is it that's broken? What is it that I need? And after that 60 minutes, that PI engages in a back and forth over chalkboard on ideation. And so each of the subgroups is going to start doing that now. We received 11 proposals, yeah. Good, okay. So the question is, what was the area of the proposals? So unsurprisingly, the present strength of the college, and this is not to say that would not be the case later on, is in artificial intelligence. There's a lot of engineering labs that are working on AI, machine learning based solutions, and that's where we received most of those applications. And then every area was well represented, and that's all we're prepared to say at this point. But it seems to me very preliminarily that AI is a natural area in which CoE and Sylvester can work together. Yes, sir. Alan. Not at all. Every department submitted proposals, and like the top performers represent 4 of the 5 present departments, no, I'm sorry. All 5 departments were in the top ranked proposals that we want to fund. That's right, all 5, including civil engineering. I mean, if a civil engineer can find a way to work with cancer, electrical, civil, industrial, mechanical, and biomedical. Yeah. Landolf, are you here? Go ahead.
So good morning, everyone. So there are some models of cancer cell that are actually basically structural models. And what we're doing is we're doing some testing to characterize those structures and the changes that happen on those cells. So our team is basically a cancer expert who can actually guide us on that process. We have basically Pranoy here, who is also from the civil engineering department, and one of our outside members, who is from the College of Other Sciences, who is acting actually as the link between what I would say, translator between us, who is actually guiding us in understanding what the cancer expert is saying. So what happens there is that that team can actually, what we're aiming to do is understand the changes, the structural and physical, chemical changes that happen on the cancer cell, and then try to characterize that with the structural, let's say, changes that happen inside the cell. So that's how we're actually going to do it. So in a way, all we're doing is creating a structure, modeling a structure, testing a structure. But how we do it and what it means is the difference.
The way I understand it is he knows how buildings are built, and he knows how cells are built, and what happens to stay there. And we have the way cancer cells are built, is different in some way. What is that? Does that mean that can be learned from buildings? That's pretty cool. And again, but they needed, as Landolf is saying, that interlocutor between the 2 teams. And it turns out a guy in physics who does biophysics was that person. Yeah. Thanks, cheers. That's all. Yes, sir. Oh, good. Yeah. Thank you, George. So that was just for the benefit of people on Zoom. That was George Grills, who's in the audience here, and he's just stressing how instrumentation needs articulated by the Cancer Center can be fulfilled by people in engineering. Cheers, thanks. Yes, ma'am. Did you have? No? Okay. Okay, that's all. And thank you very much. Cheers. Thanks, Dr. Naimer.
One, two, three. Listo? Okay, I'd like to go ahead and get the next session started. Dr. Shelik, can you initiate this next section?
Good morning, everyone. Thank you all for attending our session on advanced materials and manufacturing. So we have, I think, very exciting 18 presentations today. So I'm chairing the session with Dr. Giacomo Po, Dr. Luis Pestana, and Dr. James Coakley. So each presentation will be only 3 minutes, and we will have time for 1 or 2 quick questions after each session, while we change the presentations. But if you want to again follow up with the presenters, or if you have any long questions, please wait after the session is over. But again, we have time for 1 or 2 quick questions after each session. Also, I will introduce only the first presenter to make the flow, I guess, much better. So presenters, please introduce yourself, your department, your advisor, if you have any. With this, I want to introduce the first speaker, Bill Hixson. Please welcome.
All right. Thank you, everybody. My name is William Hixson, and I am a second-year PhD student working for Dr. James Coakley. Dr. Coakley is a premier metallurgist here at UM, and so the work that we do is, or the work that I do, is working with metals for 3D printing, particularly titanium alloys. Now, the way 3D printing for metals works is, particularly with selective laser melting, you lay down a thin layer of metal powder. A pinpoint laser melts, literally fuses that powder in a certain pattern like as designed, and it melts to what's below it, right? Then a new layer of powder is applied, and the laser scans over it, and eventually, layer by layer, you can build up a three-dimensional part. Now, the physical dynamics of what's going on with selective laser melting has particularly interest for the high cooling rate that's involved with this. So what we do, what our work does, is trying to develop new alloys for this new technology. Now, the way we do that is we'll produce an alloy, a target alloy, using conventional methods of alloying the metal, and then we'll take a sliver of that metal, run the laser over it in simulation of what it's going to do in selective laser melting, and then compare and see what microstructural changes have occurred with this alloy. Now, I have an example of two types of alloys that we've worked on, these titanium alloys. On the left is a titanium silicide alloy, and on the right is a titanium iron alloy. Now, what these images are, these are SEM images showing sort of the region where the melt from the laser, which has very fast cooling rate, compared to the conventionally cooled bulk metal. Now, on the left image, right, this is my silicide, you can see sort of running diagonally down this image. On the right-hand side, you see large needle-like precipitates. Yes? Oh, okay. Large needle-like precipitates, whereas on the left-hand side of that image, you can see the texture of what's going on there. The microstructure of the material is very different. We've been able to show that this, because of the high cooling rate, we have a significant structural difference where instead of these needle-like precipitates, we have cellular structure with the silicides with the titanium in the center. Now, on the right-hand image, this is a different alloy, titanium and iron, where you can see the melted part is on the right-hand side of the image, and the laser melted part is on the right-hand side of the image, and the conventional melt part is on the left-hand side of the image. And you can see, again, the microstructure is completely different. So the results for that are interesting. We'll go to the next slide. Right. So we can test these metals, and doing micro-hardness testing here on the left-hand side of the slide, I'm showing the micro-hardness testing for the titanium silicide, and we have a significant increase in the hardness of the material based on the change in the microstructure of the material because of the selective laser melting. So this gives us information as to the success and what we can do for developing this as a technique for the future using this alloy, because we're seeing a significant increase in the strength of the material. Now, on the lower right-hand side, I'm showing you the X-ray diffraction for the titanium iron. And this was something else that came up very interesting in our results, which is, we can show that titanium, which appears in typically what's called an alpha phase, which is a hexagonal close-packed form, when we do the fast cooling with the laser melting using an alloy of iron, we completely retain the beta phase, which is a material which is actually much easier worked afterwards. So we have microstructural changes that we're able to quantify and exhibit for these alloys that are under development for use in this new technology. This is the kind of work that we do. Our suite of instruments allow us to do all of this work in-house here. So the ability as basically this as a research showcase, we can do all of this work right here on UM. So it's a great opportunity to explore new materials for selective laser melting for additive manufacturing. Now I'd like to introduce Dr. James Coakley, my PI, who is going to give us our next talk. Thank you.
Okay, thanks, Bill. I got the feeling my student can give a better talk than I can. And I'd also like to apologize beforehand. Oh, I touched the wire. Can I get some help getting this back on the screen? Oh, there we go. Okay, so I'd like to apologize first that we have to make a quick exit. We're flying out to a conference a little later on, so we won't be around. We've got to finish making our posters and things like that. So today I'm going to be talking about refractory superalloys. And this is a new kind of materials development that we recently got funding on to pursue. So I'm going to introduce the current generation of materials and then this future generation of materials that we're working on. To introduce why we're working on it, when we look at gas turbines, we're really at the limits of materials capability. We're trying to get low-density materials with very high mechanical properties at high temperatures. And on top of that, we're trying to get corrosion resistance and oxidation resistance. So we're at the limits of materials technology. And in the back section, we can see nickel-based superalloys. So these are the high-temperature materials. They operate at over 1,000 Celsius for maybe 10,000 hours and under high stresses. And these superalloys, we've developed the same nickel-based material for about 70 years. And we have so far not been able to supplant them. We just can't beat this material's development. But they are limiting how high temperature we can run at and how efficient our engine can therefore be. So if I look at the microstructure, we have a two-phase material. You have an FCC matrix called gamma on the right-hand side, and then you have these cubes called gamma prime. The gamma can flow, and the gamma prime is a very strong material. So you can think of it almost like icebergs in flowing water, where it's hindering the flow of that deformation. So essentially, it's a composite material. You're getting the best of two worlds. You're getting a ductile material, so if it gets a bang, it won't break. But you're also getting quite a strong material because it's reinforced. So these run at very high temperatures. I'm showing on the left, you have these discs that mount your fan blades on. And we call them nickel-based alloys because on the top you see the composition. It's over 50% nickel. So this is kind of how alloys have traditionally been developed. So here we show the evolution of the material properties over the last 70 years. And you can see that we're beginning to kind of tap out of how high we can run these materials. We can run them at about 1100 Celsius. There's been major steps in development in terms of casting processes, alloying technology, but we're still reliant on nickel as our material, and we need to beat it. So this is where refractory high-entropy superalloys come in, and I've shown the composition at the top. You can see that instead of having a face-centered cubic crystal structure, we have a body-centered cubic crystal structure, meaning at the center of every crystal, we have just an atom sitting in the middle. So if you think of it as a dice, you have atoms at each end, and you have an atom in the middle. Again, they've been able to reproduce this idea of having a disordered matrix, which is ductile, hopefully, and a ordered crystal structure, which will reinforce the material. So this was quite a eureka moment, and the Air Force are very, very interested in it. So we wrote a proposal that we were going to study the development of these materials, the deformation micromechanisms of these materials, and that was fortunately funded. So this is kind of an area of research that we're going to be pursuing at UM for the next 5 years. Thank you. Next speaker is Mohammed, who is also in my group.
Thanks, Dr. Coakley. My name is Mohammed. I'm a PhD student here working with Dr. Coakley in the Department of Mechanical Engineering. And I'm going to talk about the nickel superalloys. So, as Dr. Coakley mentioned earlier, there's two phases in a nickel superalloy. You can see it on the left picture up there, the blocks at the gamma prime precipitates. And then the C is the gamma matrix. But you can also see the small dots in there, like the small particles. Those are also gamma prime, but they're like a smaller tertiary gamma prime. So as you increase the temperature, you can see it in the micrographs there. There's less and less the smaller gamma prime, the fine. At 950, you're getting none. So what's happening? They're coarsening, they're blocking together to make bigger gamma primes. So how can we study that? How can we study coarsening? You can't. So these images were taken at room temperature after the heat treatment. We can't take pictures, we can't image it during a heat treatment, during a furnace. So how would we see the microstructure and its evolution during a heat treatment? That's where in situ X-ray diffraction comes in. So we use the particle accelerator beamline at the Argonne National Lab to conduct this. So what we're doing is you put a sample in a furnace, and you put an X-ray beam, and it diffracts. And using that diffraction pattern, you can see the different peaks. And what these peaks represent is the intensity you get at planes of a lattice. Okay, so let me show you some of the peaks. I zoomed in. So if you look at the second graph at the top, this one, you can see 2 peaks there. This is a gamma prime, 2 peaks. So the smaller peak is the tertiary peak, which is the smaller gamma prime. And then the bigger peak is the bigger blocks. If you look at the one at the bottom right here, the second peak has disappeared, the smaller peak, which means this gamma primes are gone. And you can see it in the picture too. And then if you look at this peak, this shows the 3 peaks. There's 2 gamma prime peaks and then the gamma peak itself. And then you can see it here too, like it goes back to 2 peaks because there's only 1 gamma prime left. So what's this helping us with? We can see through this intensity, through the D-spacing change, how the microstructure changes, how it's affecting the properties of the material. Like when an engine is operating, how is it changing in the operation? So, yeah. So that's pretty much what we're doing right now, but we can always go forward with like other peaks and do further analysis so we can able to predict the microstructure and the properties just by simulation. Here's Jordan with Dr. Chalik.
Thank you.
Hello, everyone. Again, my name is Jordan Wright. I'm a third-year PhD student working under Dr. Emma Chalik. And what we're talking about is integrating artificial intelligence into composite additive manufacturing. And first thing I'll address is why are we so interested in using additive manufacturing to create composites? Well, if you examine a traditional composite manufacturing methods such as compression molding and autoclave, you can see that these methods use very large and expensive machinery. And then despite their immense sizes, they require very expensive, very specialized molds to create very simple geometries. But with additive manufacturing, specifically direct ink writing, we can 3D print composites and to create very complex geometries that you can't get with traditional methods, while also minimizing material waste and also improving the composite microstructure. And the improving the microstructure is directly influenced by the mechanisms in direct ink writing. So you can see here that the fibers in this composite ink start very randomly aligned with very poor material properties. But as you extrude the ink through the syringe and throughout the nozzle, the ink will experience shear thinning. And the shear thinning causes the fibers to become highly aligned once you start putting them onto the bed, as you can see in this bottom right photo. And when you compare the randomized fiber alignment and the high fiber alignment, you can see that we see that in our lab that the 3D printed composites have a far superior mechanical performance compared to their compression molded counterparts, which is great. But what you don't see is what goes on behind the scenes. Whenever you're printing with direct ink writing, it requires almost hours, no matter how much experience you have, just setting up the printing process. That's because the properties of the ink change with its environment. So for any printing session, the printing parameters used for one session it's not guaranteed to work the next session. So it changes almost hourly and even daily. But with artificial intelligence, we can automate the entire direct ink writing process. As you can see here, if we want to print a material with the desired material properties, we can train AI to basically tell us what the material is without doing any experimentation. We know the composition, so we're ready to mix the material and ready to print. Let's say we want to find the optimum parameters. With AI plus with computer vision, you can automate that entire process to where the hours the hours of calibration before printing with hands-on trial and error experimentation, that's completely automated and it's a complete hands-off experience with the help of AI. And lastly, if we want to figure out the hidden relationships between parading parameters and material performance, AI can be able to figure out what those relationships are and then be able to find what parameters maximize composite performance. And in our lab, we've seen the benefits of AI firsthand specifically for printing parameter optimization. I hope this video works. Trying not to bust some eardrums with this music. So you can see here that initially we print these lines here to optimize the print to find the optimal print speed. And it analyzes it with this USB camera to figure out the defects. And then immediately after, it takes that optimum print speed to find the optimum layer height and road width to optimize the quality of our prints. And this is done fully autonomously. You just click a button and you just let it go, which is the awesome, awesome power of AI. And you can see we are able to print these really high quality prints based off the printing parameters the AI has given us with perfect and high quality. And thank you. And I will hand it off to my lab mate, Raiden.
Thank you. So good morning, everybody. My name is Raiden Gustinville, and I'll be talking about additive manufacturing of thermoelectric materials. So I'll begin with what is thermoelectricity? Thermoelectricity is a phenomenon in which thermal energy is converted directly into electric energy, or vice versa, without any moving parts or working fluids. A typical thermoelectric module is composed of a top ceramic plate and a bottom ceramic plate, along with a thermoelectric module, which is a series of N and P-type modules which are linked together in series. And the way that we characterize this module is something that we call the conversion efficiency, which is also known as ZT, which is characterized by the Seebeck coefficient of the electrical conductivity of the material, the thermal conductivity of the material, and the temperature at which you are measuring this conversion efficiency at. So typically with thermoelectric materials, you can either use conventional manufacturing processes or additive manufacturing processes. With conventional processes, they're reliable, they provide consistent results. However, sometimes they're difficult to fabricate, there's a high cost to manufacturing them, and are limited to very simple configurations. With additive manufacturing, on the other hand, it's very cost effective, and you can do all sorts of complex shapes that can be fabricated. The only drawback is that different manufacturing processes require different pre and post methods. In our lab here with Dr. Chelik, we have successfully printed out thermoelectric modules with selective laser sintering, direct write, which my lab mate Jordan has talked about, and fused deposition molding, which is traditional 3D printing that you know about and most people have in their households nowadays. And with these technologies, we're able to achieve high levels of resolution, as you can see here, varying from micro to macro scale. On the top, we have a star, which is less than 3 millimeters in diameter, a snake, which is about 1 centimeter in length, and even larger samples, which are ranging from 2 to 5 centimeters. The most exciting part about these 3D printed modules is that we were able to achieve unprecedented levels of conversion efficiency compared to previous work. And at higher temperatures, which traditionally isn't seen in these materials, we were able to achieve a ZT or conversion efficiency exceeding 1, where most previous work for these 3D printed materials don't even surpass 0.5 at room temperature. So now, why is this all important? Thermoelectric materials play an important role, especially in energy generation, because when energy is generated, up to 70% of it is lost as heat waste. Thermoelectric materials is able to recapture this lost heat and turn it back into energy which is able to be used. And with that, I conclude. And if there are any questions? Yes. So with this specific material, it operates at a higher temperature point. So there's different types of materials, like the traditional one being bismuth telluride, which operates in that lower temperature range. So you'll get a high ZT at that point. So with this specific material, it operates at a much higher temperature point, which is much better for heat capture, because typically you don't see heat losses in that lower range as well. Oh, and yes, and with this material, it experiences phase changes, has 3 distinct phase changes, one at 400 Kelvin and one at 600 degrees Kelvin. So it exhibits different types of, different types of material properties at those different temperature points. No problem.
Good morning, everyone. My name is Giacomo Paul, and I'm an assistant professor in the Mechanical and Aerospace Engineering Department. And today I'll be talking about micromechanics of high temperature materials, which is what we do in our research group. So first of all, why high temperature materials? Well, high temperature materials are very important for a large variety of technological applications. For example, and here I have a few examples, like rocket propulsion, hypersonic flight, re-entry vehicles. And we already heard a lot today about jet engines, whose basically power output and current limit is dictated by the current generation of materials, which are these nickel-based superalloys. High temperature materials are also very important to enable very important technologies for energy production, including next generation fusion reactors, and even they may play a crucial role for the development of fusion energy. So what classes of materials are important for high energy applications? So if we look at how we could say show all the classes of engineering materials on this diagram, where we have operating limit on the x-axis and strength on the y-axis. And we see that in the upper right corner, which is the corner where we want the material to operate, high stresses and high temperature for structural materials, what we find are refractory metals and ceramics, both of which are crystalline materials, so they have a crystal structure. And what's interesting about materials, like crystalline materials, is that their properties mostly depend on the defects that we find in these structures. And the way we try to understand defects is by applying both computational and experimental techniques that range from, let's say, atomic structure, all the way from the atomic structure to the engineering scale. So here I have this plot that is typically used to represent this multi-scale effort in understanding material properties of crystalline materials. And the area in which we work in is this intermediate scale, which we call the micron level scale, so the micromechanics at that scale. And what's interesting about micromechanics is that you can, these days, you can actually perform micro-scale experiments at micromechanical experiments at that scale. And you can also compare results of those experiments to modeling. So I'll be showing now some of the results that you can obtain by microscale modeling, micromechanical modeling. And in the next talk, my graduate student will talk about micromechanical experiments. So for example, what I'm showing here is the way we study, for example, strength in the class of material that they use in jet engines, so the nickel-based superalloys. On the top left picture, you see a representation, like a virtual representation of the material that we use. And in this virtual representation of the material, we represent many of the defects that are in these materials, in particular dislocations and precipitates. And what we can study, for example, is how the strength of the material changes by varying these microstructural parameters. For example, we can vary the volume fraction of these precipitates. Virtually, we can vary their size. And we can also vary other parameters that have to do with the properties of these precipitates. One of them being the misfit strain between the matrix of the precipitate and the matrix and the matrix. And one of the results that we found is that this misfit strain, for example, is the parameter that seems to be controlling the strength of these superalloys and affects that more than all the other parameters that we have explored. We have also applied modeling to materials that are used for fusion reactors. So these materials are called refractory metals. They are ferritic and martensitic steels. And in these metals, we have completely different microstructures. We have microstructures made of little loops of these defects called dislocations. We have other structures made of voids and precipitates. And we were able to reproduce all the structures in our simulation and understand how different elements of this microstructure contribute to the strengthening and the hardening of the material. So these are some of the techniques that we develop here at These are the computational techniques that we use at the micron scale. And our next talk will now show how to verify and explore these properties using experimental techniques. Thank you.
Thank you so much, Dr. Poe. Good morning, everybody. My name is Anam Lalani. I'm a first-year PhD student, and I work with Dr. Jacques Mopo in the Mechanical and Aerospace Department. My talk today is In situ SEM micromechanics. Now, why micromechanics? The reason why basically micromechanics is a field, and it is the study of materials on a very small scale. The scale that we are talking about is in the micro and nano scale. Compared to the human hair, it is really small, sometimes really not even visible to the human eye. It has vast industry applications, and in the industrial and manufacturing sector, material development sector, and huge in the semiconductor manufacturing scale. Right now, you can see images of nickel-based superalloys, which Dr. James Coakley talked about. The reason why we do micromechanics is because we can actually observe the microstructure of the material while we mechanically test it. And it tells us a lot about the micromechanical properties of the material and helps us engineer it for better applications. As you can see in the picture, what Dr. James Coakley and his group talked about, the gamma prime tertiaries, we can actually put mechanical stresses on them and study what are their effects on the overall mechanical properties of it. What Dr. Poe does is mechanical simulations and mathematical modeling. My work is related to the experimental testing of it. And the way we do it is using an SEM nanoindenter. Nanoindentation is a technique that is widely accepted as one of the most accurate measures of determining the mechanical properties of nano and microscale materials. On the slide, you can see pictures of nanoindenters. So this device is loaded with a nanoindenter, which is a really, really small needle-like structure, and there is a placeholder for the sample. And what we do is we apply stresses on different samples to determine the mechanical properties. Here is a picture of the nanoindenter inside the scanning electron microscope. Here we can control the environment of the mechanical testing, the temperature, the vacuum, and ensure that we get the best results possible. Here is what our current research is focused on. As you can see, we deal with high temperature nanoindentation refractory metals. The temperature that we can get at is 800 Celsius because a lot of the applications of our material deals with aircraft turbine engines and nuclear scale things. So, okay. Using our collaborators at UCLA, this is the experimentation that we are performing right now in zirconium and tungsten to a temperature up to 800 degrees Celsius. We have been able to mill these nano compression experiments of single crystal zirconium and tungsten. And nano pillars have been fabricated. Using this, we have controlled the sample size, and we are going to compress it to extract mechanical properties. Mechanical properties extracted, such as hardness, stress strain curves, elastic modulus, and most importantly, the plastic flow. This can help us understand the material and then engineer it for better applications in the future. Thank you.
Hi everyone, my name is Zhiwei Yan from the Mechanical and Aerospace Engineering. And today my topic is about topic is about supercapacitors based on the nanomaterials. As we know, for now, because of the extensive use of fossil fuels, and we have the climate change problems. And so for now, the solution for the climate change is renewable energy utilization. For the development of the renewable energy, we need the energy storage device because this energy power supply is influenced by the weather, like sunlight and the climate, like this kind of things. So we need something can adapt to this fluctuation of these power supplies. For energy storage device, and we usually have battery and supercapacitors. Batteries have very high capacities, but its power density, power density is pretty low. When the high power came in, and the battery decayed very fast. So supercapacitors as an energy storage device because very promising solutions for futures. Graphite, this single layer carbon materials was used to fabricate supercapacitors because of its high surface area and high electrical conductivities. Everything, every property is these nanomaterials of this, and it's very promising to make electrode materials. However, this material is very easy to restack, and the different layers, they were bound back together. This will make the whole unique properties of these nanomaterials were lost. On the other hand, and the graphite oxide, this oxide single layer graphite, this material can disperse in a lot of solvents. So this do inspire me to propose one idea is graphite, and if we introduce another materials, redox materials, and follow with oxidation functional groups. So this compression will make the graphite. It's very this combination of these two materials can prevent the graphite from restacking when we use it. Okay, the first one is the SEM graphite of the electrode I made. The A and B is the pure graphite, and C and D is the graphite with the silicon tungsten lithium salt. We can say A and B and the restacking is happening, but C and D we can see very a lot of a single layer and transparent graphite. And this is when this electrode material was fabricated into the supercapacitors, and we can say that both resistance is pretty low. This is the supercapacitors with the graphite electrode, only graphite, and we can say its behavior is pretty low. It's like a resistor, but the graphene with silicon tungsten lithium salt. This electrode, when using to fabricate graphene, and its behaviors, it exhibited a very good behavior for energy storage. And this is a charge discharge, cyclic voltammetry under the different scanning rates. Furthermore, and I do the cycling test for more than 2,300 times. And after that, we can see the whole capacities of these supercapacitors was increased with the training. And this is the cyclic voltammetry test, and with the different scanning rate. And the picture there is about its capacitance. So we can say after training, the whole capacitance is increasing, while with the increasing the scanning rate, the whole specific capacitance of the supercapacitors increased. This is a charge and discharge graphs with these two supercapacitors, and we can say after the training and the graphic D, we can say the more energy was charged and discharged. And this is a Regonit plot of these two electrodes, and the horizontal one is the power density, the specific power, and the vertical one is the specific energy. And we can say with the power density increased, and we can say more energy was released by the supercapacitors after training, by the cycling test training. Why this happened? And we use the SEM to observe the microstructure of these two electrodes. We can say after the training and more single layer reduced graphene oxide sheet was showing up. Also, the graphic C shows the Raman shift over these two materials. So we can find the whole peaks is turning to the right, which means more single layer graphene was detected. Furthermore, and we do the calculation of these two supercapacitors. And the first equation is about this current contribution from two parts. The first part, the K1 V1 is the competitive contribution. We call it EDLC contribution. And the second part is about the battery behaviors contributions. And when we change the forms, and we can get the second equation. Second equation is become a straight line. And when we got this straight line from the picture D, and we can say the K1, the slope is become larger, which means it's EDLC part of this current contribution become larger. And also it's intercept, which means the K2, it's intercept of this, means the current contribution from the battery like behaviors, it's increased too. That means after the training, the whole capacitance or the current contribution from both the EDLC and from the battery behaviors all increased by this training. Okay, this is my result today. And the next is my lab mate, Mark. I can't hear you.
Sorry, my question basically is for the silicon, tungsten, lithium oxide material, how did you synthesize it? And then how much of it did you add to the graphene oxide to get the response of preventing the restacking of the graphene oxide?
The mass ratio is 1:1, 1:1, and then use the silicon tungsten lithium acid and with the lithium hydroxide and in the water, and then mix with the graphene, reduce the graphene oxide in, and then let them combine together and then dry.
Thank you, Juve. Good morning, everyone. My name is Mert Akın. I'm the PhD candidate of Dr. Zinyan Zhou, and I would like to first thank you, Dr. Gabriel Solo and Reni, for organizing this very engaging event, and Dr. Çelik, Dr. Paul Coakley, and other professors for organizing this session. So my talk is going to be on the safety issues of batteries and how we tackle this problem. I would like to begin my presentation by presenting a few explosion photos. On the left, you can see the Tesla Model S in flames, and the right is a Jeep in flames because of the phone explosion. And on the right, you can see the Samsung Galaxy Note 7 exploded. There are also e-cigarette explosion, and these would be spontaneous explosion. As you can see, the teenagers got hospitalized because of that. And what is the common things in this accidents? Basically, the common thing is the conventional liquid electrolyte batteries, which compose of organic and highly flammable liquid electrolytes. So these kind of batteries pose a huge risk of explosion and also pose a huge risk of fire, as well as these kind of batteries might leak toxic materials. So a question might arise how we can make safe batteries. So the answer would be one of the way of doing so is to replace this liquid electrolyte with solid state electrolytes. So in this way, you can actually make more compact and batteries with simpler fabrication techniques. But we have a challenge here. The challenge here is the low ionic conductivity of the solid electrolyte. So typically, our traditional liquid electrolytes have ionic conductivity in the order of 10 to the minus 2 Siemens per centimeter. And by definition, the superionic conductors have those having above 10 to the minus 3. So rubidium silver iodine is the class of is the material that caught our interests, and we develop our own synthesis procedure, which comprised of solid state synthesis, following it quenching and annealing, and we actually developed one of the highest ionic conductivity for this material as a University of Miami. And by utilizing this high ionic conductivity, we developed also state battery composed of silver anode incorporated with rubidium silver iodine and graphite anode incorporated with rubidium silver iodine. As you can see, the photograph of the also state battery, as far as calculators, we use graphite. So I would like to briefly show the overview of the performance. We observed very interesting behavior, which is that this battery actually outperformed in high humidity ambient environments. So that means we can effectively eliminate the use of packaging, which is the case for lithium-ion batteries. Also, we observed that the cycling, the performance of this battery was excellent. The golden standard of lithium-ion batteries is the 1000 cycle with the 80% capacity retention. Our observation was that we didn't observe any capacity fade up to 3500 cycles at the 0.5 C. So here I would like to, you can see right below the Ragani plot shows the volumetric energy and power energy density of this kind of battery, and we actually improved the performance of this kind of systems by the order of by 2 orders of magnitudes compared to the previous results. So we conclude that and envision that this kind of battery systems could be beneficial for some safety critical applications such as electronics, space, and military applications. Thank you for listening to my presentation. I would like to introduce my friend Christos, which is the student of Dr. Çelik.
Thank you, Mert. Good morning, everyone. I'm Chris Mitafidis. I'm a PhD scholar from Greece, in the Mechanical and Aerospace Engineering department. I'm glad to be here, and I'm going to present you my study related to multifunctional energy harvesting composites. Here are some pictures from the beautiful city of Ioannina, where I conducted most of my PhD research, entitled Integrated Architectures of Printed Electronics with Energy Harvesting Capabilities in Advanced Composites in the Materials Science and Engineering Department of the University of Ioannina. During my research, I participated in European, Horizon and national funded projects where we had the opportunity and the challenge to develop thermoelectrically enabled composites for autonomous structural health monitoring for the aviation industry, energy harvesting composites for residential and commercial use, as well as automated inspection of photovoltaic parks using IR thermography. Here I illustrated some of my results where I developed flexible and wearable thermoelectrics, energy harvesting composites for aeronautical applications. I conducted electrical and mechanical characterizations of materials and devices. And I have also completed in-field inspections and evaluations of silicon solar cells using infrared thermographic diagnosis. During my recent research here at the University of Miami, we developed highly conductive 3D printed polymer and resin dispersed carbon nanotubes with significant thermoelectrical properties in collaboration with Jordan Wright under the supervision of Dr. Selig at the Advanced Nanosystems Laboratory, which is a pretty cool results we have achieved already. That's all from me. I will be happy to answer any questions if you might have. And I would like to thank you for your attention. I would like to introduce you Mr. Benjamin Bessings.
Thank you very much. Good morning, everybody. My name is Benjamin Bessling. I'm the PhD candidate with Professor Yang, and I will steal some minutes from Professor Yang, so be patient with me. We love showing turbo engines. This presentation is no exception. And we have composite materials in many industries nowadays. I'm going to distinguish here and on this slide between the PMC, the polymer matrix composite, and the CMC, the ceramic matrix composite. Let's see, this is not the thing, laser pointer. Well, on the top right, you see the GE turbofan, which employs both of these materials. We have the PMC material in the front with a fan, where we need the lightweight and the anti-corrosive material properties, and the CMC material basically in the combustion chamber. Underneath, you see the Airbus A380. This airplane used 14% of its weight was composite material, which at the end they made up for 40% of the entire plane's volume because composite material is very lightweight. The interesting thing is the Boeing 787, my professor, Dr. Yang, was one of the people developing this airplane. And this airplane used 50% of its weight was composite material, which at the end they resulted in 80% of its entire volume. On the middle bottom, you see the heat shield of the space shuttle. This, of course, was a CMC material for the re-entry into orbit. On the top right, you see the wind turbine blade, which is a PMC material. We want lightweight.
and obviously big rotor blades, which are now roughly 260 meters. These offshore plants in height, as in comparison, the Eiffel Tower is 326 meters high. The only reason that we can create these huge structures offshore and harvest that much energy is actually through composite materials, because traditional materials would just fail under their own weight. And representing basically all our sports gear, the bicycle on the bottom, we now see composite material in sporting goods or even in just as accessories. I'm going to take some more minutes. Here we see a photo that Professor Yang took in Belgium of one of the wind turbine blades that actually failed. So since it's a new material, these things happen, and we are still trying to understand why these things happen. Many of you probably know 9/11, but a couple months later, there was another plane crash in Queens, New York, where the American Airlines Flight 587 crashed due to the separation of the vertical stabilizer in the back. This was due because as you can see in the bottom, I don't know how the laser works here, but the connection between the vertical stabilizer was connected with metal pins to composite material. Over time, we had fatigue, which just caused the complete separation of the stabilizer during takeoff, which caused the crash of the entire plane. So to understand the material better, we have to, of the entire airplane, we basically have to go down and analyze step by step to understand actually what is happening at a micro level. So if we look at the small window here, we see in black, these are small cracks that develop inside the plane. Let's say it's the window. So the question is this now a safety issue or is it not? And if yes, can we replace it? So what Professor Yang did is he went to basically the micro crack level and analyzed these cracks that develop here on the, I still don't know how the laser pointer works. Not this point. Okay, it doesn't matter. So we analyze it step by step. We do this to predict the life and reliability of these new specimens. By doing these virtual tests, we can reduce the amounts of experimental tests needed and therefore reduce the costs. This was supposed to be a video file. Jordan was able to do it. I was not able to do it. So you would see on the top that was the video file. And on the bottom right, on the bottom, you basically see the result. You see this is a compression test for a Boeing part with a notch inside. And you see a very complex failure behavior. These white lines represent all cracks. So as we are compressing this, different cracks and different plies, since we have different fiber orientations, different cracks develop. And we were able to see, if you look on the top right, we have their analytical and our 3D AFEM results, that our results were very much in agreement with the tests from Boeing. I'm not allowed to show you the real results, but these are normalized. So to summarize everything, we can have a complex progressive failure behavior which demands physical-based high-fidelity modeling capabilities. The AFEM code is capable of predicting complex progressive damage solutions, which results in fewer tests needed. And the AFEM-based virtual testing designing of heterogeneous materials is able to do this with complex microstructures. Thank you very much for your attention. And the slide is stuck. I don't know who's next. I think you have to help me. I can't switch to the next slide. Well, it's enough time to read the slide completely. You know how to switch the slide? For some reason, it's completely stuck. Probably because I tried to use a laser pointer. Otherwise, the next presenter? Yes, it's working again. Thank you, Frank.
Hello, everyone. My name is Mingyue Wu. I'm the second-year PhD following the Dr. Pastana. So today my presentation is about learning how glasses creep. So actually, the glasses we are enrolled in our study they are defined as the disordered systems with the fractured dynamics. So the glasses in our study, they are not only included the normal glasses we see in our daily life, and they also included the other materials like the cement and the other metallic glasses. So here I show the pictures of how they look like, and they are nanostructures. And the creep phenomenon, here it is the long-term plastic deformation of the sustained load. So here I showed in this picture. So when we applied load to the system and put it for a time, and by the end, when we release the force, and actually we could see a permanent deformation compared to its original configuration. So that is actually what the creep. And here you could see in the right-hand side, I show the actual creep phenomenon happening in our daily life. So actually those creep phenomena, they actually limit the lifetime of our structures. So our aim is to tackle this problem. However, the biggest difficult things to study the creep phenomena is like we don't really understand how the creep dynamics, how they depend on the glass structures. So we need to shift our attention from those big concrete bridges to actually the nano cement particles. So this because the macroscopic creep behavior actually depends on the microscopic of the displacements of those nanoparticles. So in these slides, I show our basic methods to tackling those problems. So we use the molecular dynamics system, the Anderson model. We try to apply different loads to the system and to simulate how the nanoparticles move. And for the outputs, we're going to get the different displacements of each particle as a function of time. And then finally, we're going to use machine learning regression models to predict those nanoparticle displacements. Because the machine learning, they are a very good technology. So we could gain insight of their connections between the nanoparticle movements according to different times and forces. So thank you very much. And I welcome my colleague again. Okay.
So I'm assuming that's CSH, right? So.
So it's the idealized particles. It's not the real actual CSH elements in that.
Okay. So how did you decide on the size of your cell?
So here in this system, we use choose 10,000 particles in those sites, and then in the CoE model, we choose 2 types of the atoms. So that's basically to simulate the CSH gel, but they are not actual CSH.
Hello everyone, I'm Geng Yuan. I'm a PhD student working with Dr. Pastana. And my topic today is about the study and rational design of high entropy alloy catalysts. High entropy alloy, they are relatively new materials made of at least 4 principal metallic elements combining comparable proportions. So they have a high level of configuration disorder. And if you look at their surface, the high tunability provided by their large diversity of potential reactive sites has made them very attractive materials for the catalysis applications. Because through this high entropy alloying, they are able to modulate the bending energies. The bending energies describes the interaction between the reaction intermediates and the catalyst surface. And based on the Sebastian principle, it is well known that the highest catalytic activities is correlated with the ideal or optimum bending energies. So given that high entropy alloys, they could display a myriad of local environments. So they can show almost like continuous coverage of the bending energies. And this almost continuous distribution of bending energy on these high entropy alloy surfaces can ensure the formation of bending size with the ideal or optimal bending energies, therefore corresponding to the highest catalytic activity. However, the design space of high entropy alloys as catalyst will make their experimental design less efficient. Why? Because first you have to consider numerous elemental compositions. Even if you only focus on the Earth's abundant transition metals, and you want to make an alloy with only 5 different elements, you still have thousands of elemental compositions to choose. And for each elemental composition, you also need to consider numerous atomic ratios because they also have an effect on their overall properties. So when you consider both of them together, you will have an incredibly vast design space of these alloys, which could make your experimental screen unfeasible. So to better address this issue and motivated by the recent applications of molecular modeling that have offered the opportunity of the in-silicon prediction of advanced catalysts, we are applying computational approaches in our study where we'll use molecular modeling simulations in conjunction with the machine learning process to give us more insight about the catalytic properties of these alloys and to make better design principles that could facilitate fast and accurate catalyst selection, and that could be used reliably to guide experiments. And that is what I've been working on, and thanks for listening. And I'll introduce next speakers, Dr. Pastana. Thanks.
All right, hello everyone, good morning. My name is Luis. I'm an assistant professor in the civil engineering department, and in my lab we use molecular simulation tools to try to develop better materials. So I'm gonna explain to you what that means. The traditional paradigm of material discovery and design is basically first by accident, like champagne, and then we basically optimize function by trial and error, and that trial and error driven primarily by experimental efforts. So this is a slow, expensive, it's unreliable, it's also very limited, right? You are limited to things that you can actually make today. The paradigm of that is Edison, that he basically found the metal for the filaments in the light bulbs just by trial and error. So what's the alternative? The alternative is really use computation and models to develop fundamental knowledge. What that means is that if we understand the structure-property relations at a very fundamental scale, we will be able to design better materials without having to even manufacture them first. And this was recognized, obviously. So in 2011, there was this big program with a lot of money called the Materials Genome Initiative that was trying to push this forward. Okay, and this method is supposed to be faster, cheaper, and unlimited. Don't confuse this approach with saying that we don't need experiments anymore, right? Experiments are fundamental in the feedback to make this work. So you cannot see because the zoom stuff is hiding the title, but the role of molecular modeling and molecular structure. So why do we care of how things behave at the atomistic molecular nanoscale? So on the one side, we have nanomaterials. You probably are all familiar with those. These are directly relevant. These materials have amazing properties, and the amazing properties come directly for how they look at the nano-meso atomistic scale. But then even macroscopic materials, things that you see, you touch, they make buildings of, like concrete or spider silk. All these materials have very complex hierarchical structures. All right, and the final properties at the macro scale, they depend on how these materials arrange themselves at these different scales. And at the very bottom, you have atomistic scale and nanoscale, right, at the level of molecules. And to gain insight into how these materials behave and understand where their properties come from, again, the aim is to really figure out those mechanisms so that we can make them better. We need tools, right? So that's what we do in my lab. Okay, those equations look terrible. So what we do, the workhorse for our approach is atomistic simulations. These are, there are many flavors, okay? But the idea is that you represent the system at the atomistic scale where each atom is a point particle. Now the atoms interact with each other, and the dynamics of the atoms are just governed by classical mechanics, okay? So with that, the key question here is how the atoms interact with each other, right? That says that if your system is silicon glass or is some sort of iron or is a biomolecule. So this technique allows you to simulate the broader variety of materials that I can think of any technique. So you can simulate proteins, you can simulate metals, polymers, composites, ceramics, clays, glasses, pretty much anything. The limitations are obviously the scale, right? You are, for good or for bad, limited to the nanoscale. And in my lab, we use these tools and other tools, but always computation, to really gain insight into a variety of problems. Again, presented to you the issue with Catalyst. We are focusing on some systems that are complex. What that means is that either their structure is very complicated, like in glasses, or their configurational space is very vast, like in high entropy alloys. And in those problems, you can benefit from data-driven approaches as well that we are starting to use. We are also interested in extreme, mechanics, shockwave propagation in materials, and biofilm mechanics. This couldn't be at the nanoscale, but we are very interested in how the biology actually affects the mechanics, and the mechanics fits back into the biology. So with that, I'm going to close with this quote that I really like, because if you do computational stuff, you have to always keep in mind that a computer lets you make more mistakes faster than any invention in human history, with the possible exceptions of handguns and tequila. All right, so thank you. And I'll go to the next one.
Hi, my name is Ying Wang. I'm a third-year PhD student working with Dr. Purnoy Sornani, and I study civil engineering materials. My topic today is about the activation of basaltic materials for use as supplementary cementitious materials. So what is basaltic materials? It's basaltic rock. It's a major waste from US quarries. More than 1 billion tons of waste rock are generated yearly in the US quarry as quarry finds. And the high volume disposal options for such waste rocks is unavailable now. They are going to landfill. It's a huge waste. But wouldn't it be a great thing if we can use these waste rocks into construction materials? But such materials are crystalline, and therefore they cannot be used in the concrete as is. So the question is, how can we activate these materials? Probably by modifying their crystallinity through the activation pathways. We have two pathways to activate these basaltic finds. The first one is thermal activation, which is by heat. The crystalline and inert SEMs can be activated by heating beyond 1200 degrees and cooling. The heating, especially the temperature beyond 1300 degrees, can result in global melting of this material, and it can create subsequent amorphization, which means reactivity. If we take a look at the figure, the original basalt cannot pass the reactive threshold, which is the red dotted line. But after we treat it using high temperature, beyond 1200 degrees for more than 1 hour, all the materials can pass the reactive materials limit. And if we take a look at the XRD figures, the inert basalt, they are very crystalline with all those crystalline peaks. But after we treat them using thermal activation process, most of the crystalline peaks are reduced or are gone because the amorphization is happening globally. That means the materials, they are reactive. Another way to activate this basaltic rock is by grinding, which is mechanochemical activation. The crystalline and inert SEMs can also be activated by high energy grinding, such as for 30 minutes of 400 RPMs, planetary ball mill. The increased fineness and localized and heterogeneous amorphization is creating the reactivity of the basalt fines. Let's take a look at the figure on the left. The heat release of all the treated materials are increasing with the grinding time for different type of rocks. The basalt, 2 different basalt and 2 different mine tailings. Those are all waste materials. Nobody wants them, but we are turning them into reactive materials, and we can utilize them in constructions. And same case for the XRD curves. If we take a look at the regional, a lot of crystalline peaks. But if we grind it using high energy mill, for 15 minutes at 400 RPM, the crystalline peaks are reduced a lot. That means the amorphization is happening. And that's how we activate this waste material and turn it into good materials. And now let me introduce my advisor, Dr. Sornani.
Thank you. Can I get that? This next. All right, thanks, Ying. So my name is Pranoy. I want to talk about a little bit of what we do in the lab, and I'll talk about calcium aluminosilicate glasses, but I'll also keep it pretty broad. First, I'd like to thank my sponsors. They're on the right. Without them, we wouldn't be working in the lab. More importantly, I'd like to thank all my students on the left, because without them, there definitely would not be anything to present. So several of them are here. Thank you, guys. Keep up the great work. I just come to conferences and talk mostly. So all right. The problem we are tackling is supplementary cementitious materials. We design new materials using some fundamental approaches. To do this, we work with Luis. That's a funded NSF project where we're looking at multi-scale mechanistic understanding of these systems which we're modeling as calcium aluminosilicate glasses. We also take very applied approaches, which I'll describe in the next slide. But the reason this is important is we make about 30 billion tons. Not so much, but about 30 billion tons of concrete every year. That has huge impacts associated with it: electricity, energy, CO2 emissions, etc. We want to cut these down. There really is no other way to do it than reduce cement consumption. So that's what we do. We work on low carbon cementitious replacements. A lot of this is very collaborative because it's a complex, multi-scale, heterogeneous problem that we are trying to solve. So one of the things that we are the world experts in is in developing new reactivity tests. So essentially, all these is they're saying that we take a glassy calcium aluminosilicate material, we react that material with a high pH solution and a source of calcium. And then we measure various properties. These could be dissolution, these could be heat, these could be calcium hydroxide consumption, strength, whatever. It doesn't really matter. But civil engineering is sometimes a low-tech field, so you have to develop foolproof tests or idiot-proof tests, if I can be rude, We've developed a lot of these tests, and the first test that we've developed, the bulk resistivity index test, Ying worked on it, and so we actually won a Best Paper award for that. Then the second test that we developed, this was through my postdoc till now, we've had really a lot of great publications on that. It led to me winning the Rylem Gustavo Colonetti Medal for Outstanding Achievement. We've also developed a low-cost version of this reactivity test. So all sorts of tests, if you're interested in reactivity, we are the people to do this. Now, what are we doing with the calcium aluminosilicate glasses? Well, one of the things we're doing is measuring their reactivity. But before you measure reactivity, you've got to synthesize these guys. So we've synthesized some glasses, you can see that on the right, which are representative of commonly occurring materials. But we've also synthesized some glasses with very unique compositions, glasses that no one in civil engineering has ever synthesized before. And we get really interesting. Interesting is a loaded word, right? Because sometimes it means good, sometimes it means bad. So we get a lot of interesting data which we have to analyze. Half the time we don't know what exactly it tells us, but we are persistent. We spend a lot of time in trying to figure out what the data is telling us. So that's what we're doing. But Luis made the great point, right, that a lot of this is trial and error. So we work very closely with Luis in basically making sure that there's a feedback loop between the experiments and the modeling. The results are pretty preliminary at this point, but it's known from literature that the reactivity changes in a complex way based on the glass composition. It depends on disorder, which calcium and alumina induce. That is clear, but we also see a complex effect on the kinetics, and that has not been studied. We're trying to figure out what is happening with the kinetics at this point. Now, I realize that this is research day, but outreach and education is extremely important to us, and I find myself spending an increasing amount of time on outreach and education. So we do this through several different activities. One is seminars. So we organize the department seminars. Several of them include speakers on sustainability. We do this for the NSF project and for internal Uling projects as well. All of these go on YouTube. You know, you can check me out on YouTube. I'm not a popular YouTuber, but we try to educate people through our YouTube channel. We also have consistently had school students visit us. We also visit the schools. We've developed course modules for the school students as well. And the bottom line is, you know, the diversity issue in STEM, especially in civil engineering, is pretty obvious. Everybody talks about it, and you know, it's not something that can be tackled all that easily. But we believe that with prolonged and sustained efforts in showing middle and high school kids how cool STEM is, what are the awesome things that we're doing at ultimately they will become engineers, and this is what we want to do and what we are doing. There are other outreach efforts as well, through which, you know, for example, we organize symposia, journals, special issues, which I'm editing, etc. All of these are happening. I would be more than happy to discuss with you both our research and our outreach efforts. We are highly collaborative. And, you know, when I came to concrete was what I did, but is fantastic. We have so many interdisciplinary efforts. Everyone is willing to collaborate. So somehow now I also work on seawalls, on bones, on corals, and cancer. I'm not an expert on any of these topics, but by working with you, I'm happy to learn more about these topics, and maybe, you know, we actually work together to submit something, to make something better happen. So thank you very much. I have no idea who the next speaker is, but.
Hey everyone, I'm Sadiq Taleh. I'm a first-year PhD student working in Dr. Gharimanejad's lab. And today I'm going to talk to you about how we're using machine learning to design new admixtures for concrete. So basically, this project is that we're using biomolecules, specifically proteins, to increase the air-entrained porosity of concrete. This means higher volume of air and also a well-dispersed structure of pores. We have two main objectives. The first one is that we want to understand how these proteins interact with cement and other hydration products in the mixture. Because in solutions, in ionic solutions, these have been studied a lot in colloidal science and other disciplines. But when you add particles, cement particles, and so on, these interactions become very, very complex. So we want to understand that. And as you can see in the bar graph, the green foam height and the blue cement porosity, they don't have any correlation because these environments are so different. Our second objective is to develop a machine learning model that can help us engineer and predict new proteins. So this is a micro-CT scanner that we're using to characterize the pore structure of our cement. And it's a very valuable tool because it allows us to measure pores as small as 10 microns up to 1,000 microns, which is the range for air-entrained pores. This is a bit expensive device, and the measurements that we do with it is expensive, but it's a very valuable tool that we're using. So this is the general scheme of our machine learning model. In the first layer, we have the molecular properties of proteins and biomolecules, things like hydrophobicity, solvent accessibility, and so on. These are the inputs that we get from the protein structure that we have. We're going to connect this first layer to the second layer, which is the physiochemical properties in the cement mixture. This is more or less the macro scale. Things like surface tension, absorption to the particles, charge, and so on. And in the output layer, we have the air-entrained porosity or pore structure of our samples. Things like air volume, how well dispersed these pores are, and so on. Most of our work is focused in this section. We're doing a lot of tests on each of these layers, but I'm going to skip all of these because we don't have time. So the good thing about this machine learning model is that it enables us to design new materials. This is related to what Dr. Pestana talked about. In the first section, we're discovering proteins properties using trial and error. But when we develop this machine learning model, we can actually screen the protein data bank, which has around 150,000 registered proteins, and we can find the most optimum proteins, and also we can predict the properties of any imaginary biomolecule that we can synthesize. This is the power of this approach that we're taking. You can reach me here, and thank you. And I want to introduce Dr. Qahramani Nejad, my PI. Thank you.
Thank you, Sadaq. Any questions for Sadaq? Okay, today I'm going to talk about bio-inspired self-heating concrete. This is the work done by Elvis, and last night I asked him to let me present his work. I hope that he's not upset about that. So there are many examples of nanocomposite materials in nature with properties, mechanical, functional properties, well exceeding those of the engineering materials that we know. One example is the image that you can see in top right. This is a mussel, and this has the ability to adhere to various surfaces under various environmental conditions. The adhesion is so strong that sometimes when people try to clean the surface, it peels off the substrate. And it turns out that this creature is able to have such high performance adhesion through certain proteins that it produces. And it is because of these proteins that are able to achieve such high performance adhesion. And here you can see an image of that. And to the left is probably the most widely cited example of a nanocomposite. It's nacre, which is the inner layer of a seashell. It has one of the highest fracture resistance that we know. So this material to the left, nacre, is primarily 95% made of highly brittle calcium carbonate. Calcium aragonite phase of calcium carbonate is highly brittle, but because it has about 5% biomolecules, the nanocomposite is able to achieve such high fracture resistant performance. It is because of these biomolecules that are present in the material, and they are the ones that are important during the nucleation, microstructure formation, and properties of these nanocomposite materials. So the idea here is, can we look at nature, can we copy from nature, and see if we can induce self-healing in concrete. When you break your hand, you don't do anything. You just put it in cast, and your body is able to heal itself. One of the primary materials used is calcium phosphate. That's what acts like a glue. So what happens in concrete is that concrete has a lot of calcium ions in it. Once a crack occurs, you have CO2 coming in from air, or you can introduce CO2 through other means. So you have calcium ions, you have CO2, you mix them together, and then what you get is calcium carbonate instead of calcium phosphate. And this acts like a glue, fills the crack, and over time heals the crack. This process happens in concrete naturally, but it takes a very long time. So what we do, we are going to use certain biomolecules and see if we can use them to tune the nucleation, microstructure formation, and as a result, the adhesion and mechanical properties of these calcium carbonate phases. So that's basically the idea. So here I'm skipping a lot of work that Elvis did, and I'm just showing the load recovery. Let's say you have, you take a sample, you crack it, and then you cure, or you let concrete cure itself. Here you see different samples. Control is the one without any proteins. And the other 5 samples are those that we incorporated proteins in them. So control, as you can see here, let me see if I can get the laser. So the control is the left one, and you see that its load recovery is very low. But when we incorporate certain proteins, whey protein, albumin, NFMP, SPI, I'm not going to go into the detail of these different proteins, we see an increase in load recovery, which is a measure of healing. But when we had collagen peptides, CP, it didn't work. So certain proteins work, certain proteins don't. So I'm going to go to the next slide where you're looking at cracks before and after healing. So in the case of control, we don't see much of a feeling in crack. But in the other 2 cases, in the case of, so NFMP is non-fat milk protein, and SPI is serum-based bioglobulin protein. So you see before and after, in the cases of the 2 proteins, we see a partial feeling of the cracks. So as I said, we have done a lot of other characterizations. I don't have time to go over them, and with that, I'm gonna conclude. And again, this is the work done by Elvis, who's sitting right here. And if you have any questions, he's more than happy to answer the questions. And I think I'm the last speaker. All right, thank you for, I'm gonna thank the organizers for putting this together, and Helena and the other members.
All right, thank you everybody for coming to the session. I think you all know where the posters are. It's just next door through the patio. And if you saw something that you liked or you want to contact anybody that gave a talk, please feel free. I think we'll share the slides. So thank you.
outside. I just realized that I did not understand.
Let's wait for Elena.
Okay.
This is another microphone.
Okay. No. I don't forget it.
Okay. You need to log in.
Elena?
Okay, I'll make an announcement over the poster session to see if we can get.
Yeah, can you just log in the meantime so we can...
Oh.
This is it.
No.
Let me see the bigger.
No, just close it. It's one of these.
No. This is it.
No, it's this one.
Let me see the bigger.
No, just close it. So if you want, huh? You want to say some words? We're starting now? Oh yeah, yeah. In 2 minutes. You want to say something? I don't know. Like I don't care, but I can say something. Sure. Just one word, one line. Do we need a bar or do you think it's kind of disturbing for the students? Some people will probably come and look at that. Oh, can you turn it off? I know Helena is doing that. Okay. We're just waiting a few minutes for people to come from the poster session. So let's just give them a few minutes to finish their cookies and finish talking at the posters.
Can you just turn it off? Yeah. But can you turn it off because this is? Yeah. Can you just leave it like that? Yes. Thank you. It's all good. Okay, we almost reached the Miami 5 minutes, so let's just give it another one more Miami minute, and then we'll start the session.
Because I had some relations, I don't know whether
but
you were able to open it.
Yeah,
not right now.
Yeah.
Yeah, it's okay.
Okay, I think we'll start. My session co-chair went to gather a few people, I guess, that were still struggling around, and I guess he forgot to come back, but I'll start without him. So on behalf of Dr. Kizroev and myself, welcome to this afternoon session. We have a very exciting session on health applications, and it covers a broad range of topics. As you can see here, starting from retinas on a chip, all the way to nanoparticles that manipulate your brain, all the way to electrodes that are implanted in the brain to do strange things to you. So hopefully we'll have an excellent session combining, showing you and illustrating all of the different applications of engineering and medicine. And the first talk is by Emma Drabel. So just before while she's coming down to talk, so these talks are going to be again rapid fire, 3 minutes, and we're going to strictly enforce the 3 minutes. So make sure that you stay within time, and we'll have time for 1 or 2 questions, brief questions after each presentation. So Emma, first presentation is by Emma Drabel on retinoblastoma on a chip.
Okay, so my name is Emma. Every year, hundreds of kids suffer from eye cancer, which results in loss of eyesight, loss of their eyes, and even in death. So,
yeah, we just realized that the screen is not on screen here, so he's going to get
oh, don't worry.
so that the audience can see. Yeah, thank you.
Yeah. Okay. So every year, hundreds of kids suffer from eye cancer, which results in loss of sight, loss of their eyes, and even in death. So if we can develop drugs against eye cancer, this would make a really big impact in these young kids' lives. But in order to make a drug for eye cancer, we need to know where this cancer comes from and how it progresses. We need to know what we need to attack. And we don't know that yet. So in order to study this cancer is really hard, because this cancer starts developing when the baby is still in the belly, and it's also really hard to use animal models for this research, because the animals' eyes don't mimic human eyes, and also these animals don't develop the same eye cancer as humans do. So my mission is to make the first ever laboratory model to mimic retinoblastoma, and we do that using retinal organoids, eye organoids. And by growing these eye organoids from a single cell into this like mini tissue, we can study how this cancer starts and how it progresses, how it develops, and eventually know what we need to attack. But to grow these cells, we need to tell the cells what they need to become before they can become a retinal organoid. And this process is done by signals. So we give the cell certain signals so it knows that it needs to become retinal cells. Okay. So telling the cells what they need to become in this case is really difficult, because the environment of the human eye is very complex. It has many different cell types in an organized manner, as you can see here. And we need to apply different signals at different time points and at same time points at different locations in the tissue. And one of the most important signals of the human retina is the oxygen concentration, because the outside of the retina is perfused with a lot of blood. And I don't understand. Yes. The outside of the retina is perfused in blood and has high oxygen concentrations, while the inside of the retina sits in an oxygen-free environment, so it doesn't have any oxygen. So you can imagine there is this really steep oxygen gradient over these few hundred micrometers of the retina. So therefore, I made a device, I think this one, that mimics the human eye environment, including these different oxygen concentrations. So we can grow these retinal organoids in the oxygen gradient and hopefully see that all these different cell types from the retina will develop in the same organized manner. So this device can hold up to 60 of these organoids and will mostly be connected to pumps. So the pumps apply a culture media change and will apply the oxygen gradient in the wells. And so far the results look very promising, and hopefully we can soon start doing research on this retinoblastoma tumor and come up with a drug to save the lives of hundreds of kids each year. So thank you very much.
Any questions? Yeah, question.
Emma, what are you doing tomorrow?
Next step.
Tomorrow I'm riding the Dolphin Challenge Cancer Ride to raise money for cancer research. If anyone wants to support.
Great. Good luck. Next presentation is by Kevin Davis from Dr. Prasad's lab.
And then how do I move it forward? Okay, perfect. Okay. Hi, I'm Kevin Davis, and I work in the Neural Interfaces Laboratory under Dr. Abhishek Prasad, and I'm excited to briefly share our patient-operated brain-computer interface for hand grasp restoration that we did in the home. There's currently a need to treat paralysis. Paralysis is the lack of ability to move the limbs. And we know that there's 5.4 million individuals who currently suffer this reality in the US. And besides the medical issues, there are significant financial and economic burdens that are placed on these individuals, their caregivers, their families, and as a result, public health. And lifetime accrued costs can grow over time as they continue to need dependence on caregivers. And so any improved function that we can give them really can cut back on some of these lifetime costs. And while there's no current treatment for paralysis, we know that brain-computer interfaces have a promising opportunity to restore some of that function by giving direct brain access from the brain to a computer machine. These current demonstrations that have been done have largely been done in the laboratory setting, and there's a need to assess these and evaluate them in the home environment to evaluate their performance. So our goal is to develop, deploy, and evaluate a mobile brain-computer interface into the home of a patient with spinal cord injury. And we know from surveys that individuals with quadriplegia, or they can't move all four limbs, really desire arm and hand function. And so we implanted a patient with a system to record their neural data from their brain, sent that data over to a mini computer that would then control a robotic glove that they could wear. And then we packaged all of this onto their wheelchair so they could take it home, and developed a mobile phone application for their family or themselves, if they can, configure the system at home. And this video demonstrates the subject's sibling actually setting the system up. It's important to make sure that these systems are not a burden on the caregiver or their family, otherwise they won't use them long term. Comparable studies after extensive training usually get these systems set up within 20 to 30 minutes, and after a week of studying we found that they could set this up within 5 minutes. Another important distinguishing factor here is that they need to be able to train the decoder to detect what they're thinking. And usually that happens, they need to do that every day. We only had to train it once, and our decoder is actually showing relatively stable accuracy over time over the last 1.5 years. And this video here shows them actually picking up their headphones with this system. Our future direction is looking at more functions for this beyond the binary open and close, looking at how someone who has spinal cord injury re-engaging their motor cortex affects on neuroplasticity, and then potentially how that might be used in rehabilitation. With that, I'd like to thank the huge team that has been involved with this since its inception, and thank everyone for listening.
Time for questions? Any questions? Yeah.
So what do you measure when you have accuracy on the
So, yes, he said, what are you measuring on the y-axis in terms of accuracy? So this is a simple classifier, so we're looking at the brain data and it's coming out as open or closed, so we're looking at
what is the predicted value based off of his brain measurements to what it should have been.
Next presenter is Elric Zhang. Sorry. Let's see if I can get the hang of this now. It's my presbyopicals. Okay. How do I share the screen all the time instead of sharing presentation? I don't know why it's not doing. Yeah, I got it.
Can you share the screen? Screen. Up, not presentation.
We got there. Sorry.
Hello, I'm presenting on behalf of my colleague Elric. Okay. Today I'm presenting magnetoelectric nanoparticles for wireless brain stimulation. We use magnetoelectric nanoparticles like tiny little. Oh, this goes so fast. Okay. As a quick overview, I will first cover the theory of our research, followed by explanation of our experimental setup, and give some recent results. We use magnetoelectric particles like tiny little electrodes to trigger the neurons. If you alternate the magnetic field around on the particles, they will generate small electrical field around them, and we can use this electrical field to trigger the neurons. Our goal is demonstrate controllable neuron activity with the magnetoelectric nanoparticles. Our experiment setup is fairly simple. We send magnetic pulses and compare these results with standard electrode firing of the same neurons. At the end, we also do control measurement with insertion of TTX, which inhibits the activity. With the right signal parameters and dosage, we were able to get neurons to fire with the magnetic field. Here shown here is the time traces of. Can I use pointer? Oh, okay. Shown here, we see when the magnetic particles are not present, we don't see magnetic response. We don't see the neuron firing with the magnetic pulses. The blue lines represent here is the time of the magnetic pulses, and the red for the electrical for the same. At the bottom, you see every time we send a magnetic pulse, we see a neuron firing. On the left side, we see an average magnetic and electrical response of the couple of neurons. Here we see the spike train analysis of the entire zone of neurons. Each dot here representing a neuron firing event, darker dots meaning the stronger firing. You see when no particles are present, there's only random firing with the magnetic field. But when you apply the electric field, they are aligning with the electrical field. At the bottom, when you apply the magnetic field over the coercivity of the magnetoelectric particles, we see in highlighted area that they also align with the magnetic pulses. So as a control, we add TTX to inhibit the activity, and we don't see any electrical or magnetic response with the applied fields. So what is next? We started our in vivo studies for the same thing, but in the meantime, we are still doing experiment on the cell culture to increase our response rate to optimize the parameters. In the long term, we want to move beyond triggering neurons to start thinking about how these particles can be used to solve real life problems like paralysis or other neurological disorders. Thank you. Any questions?
Next presentation is by Diana Veluto, if I can find it. Okay.
It's not
showing? Forgot.
Yeah. Now shared. Thank you. It's fine. Yes, thank you. Hello everybody, my name is Diana and I work at the Diabetes Research Institute of the University of Miami, and I will briefly talk about my research in nanotechnology and diabetes, which focuses on preparation of nanomaterials for targeted, localized and sustained drug delivery for the specific application in preparing localized immunosuppression system for pancreatic islet transplantation, which is the only cure for type 1 diabetes. So for who doesn't know, nanomaterials can be very useful to prepare drug delivery vehicles. They work like nanofedex in the human body to improve pharmaceutical compounds. So I aim to do that as part of a bigger project to ensure that transplanted pancreatic islets survive, using my smart chemical tools, which I renamed after my name, Diana's, which stand for drug integrating amphiphilic nanomaterial assemblies, and are made of synthesized by myself amphiphilic in the lab amphiphilic block copolymers, which are biocompatible and also very stable, and they can form in water different aggregates with different morphology, which are described on your, which are schematized on your right and also imaged on your right. They can form micelles, fibrils, vesicles, and they allow very rapid and stable incorporation of different kinds of drugs, hydrophobic or hydrophilic. And most important, they can target and be uptaken by different kinds of cells, all the kind of cells, including immunocells, because of their very small size, which is between 20 and 100 nanometers. Here I summarize quickly some results from two different preclinical studies. One was done with cyclosporine, this is published, and the other is in preparation with dexamethasone, which are both hydrophobic drugs. Cyclosporine is completely insoluble in water, but using my nanomaterials, I was able to solubilize a great amount of this drug in water, about 55 milligrams per ml. Plus, the nanoparticles provide also sustained release of cyclosporine, allowing also to reduce its dose in vivo. Injecting the nanoparticle containing cyclosporine locally in vivo in the subcutaneous space, we observed that the nanoparticles accumulate, they drain quickly and directly into the lymph nodes, allowing basically regulation of the immunosuppression only in the local sites, so in the lymph nodes, and also allowing like this reduce dose, reduce administration frequency, and of course reduce side effects. With the dexamethasone, we use a very simple local inflammation model in mice using LPS injections, and we injected the nanoparticles containing the dexamethasone systemically by IV injections. And we observed that the nanoparticles circulate in the blood from stabilizing the drug for a few days, at least 48 hours, and then as soon as the inflammation triggers, they accumulate in the site of inflammation. And we observed this using ProSense, which is a probe for inflammation, and using the whole body imaging, live imaging. So we have different options using these nanomaterials called Dianas. We can integrate them directly in the islet transplant site, but we can also inject them locally, subcutaneous to target the lymph nodes, or systemically IV target for targeting the site of transplantation. And because of their versatility, we can test different combinations of drugs in order to develop, localize, and sustain the immunomodulation for survival of transplanted islets without side effects of the immunosuppression. And we hope the final goal is to translate these Dianas in clinical practice. And with this, I thank you all for the attention.
So these will be called Diana mice, correct?
Yes.
Next presentation is by Giancarlo Tereda.
Hi everyone, my name is Giancarlo Tejeda. I'm a member of the New STEM Lab with Dr. Courtney Dumont, and I'm going to be talking about my project developing scavenger nanoparticles to sequester inflammatory signals. So, spinal cord injury occurs when trauma is inflicted directly to the spinal cord, causing irreparable damage and impairing at and below the site of injury, as seen here. After sustaining an injury, the spinal cord has a limited ability to regenerate and suffers an intense inflammatory response. This inflammatory response is can cause secondary injury and further damage to the surrounding tissue, and can lead to intense scarring that occurs and is inhibitory to repair and regeneration of the spinal cord. So to treat this intense inflammation, I'm developing a scavenger nanoparticle system to act as a sink for these inflammatory signals that would capture these signals and capture them to their surface of the nanoparticles. I'm developing these nanoparticles with polylactic glycolic acid and polyethylene glycol, along with chondroitin sulfate, which is a biological molecule that is found in the extracellular matrix. The chondroitin sulfate's chemistry allows for the nanoparticles to have an affinity to the inflammatory signals and attach them to the surface. Then, once they are attached to the surface, they will be cleared by immune cells that are already at the site of injury, attenuating the inflammation that occurs. The intended outcome of this therapy would be to reduce the inflammation that occurs in acute spinal cord injury, the secondary injury that occurs, and the cystic scarring that occurs in the long term after spinal cord injury. By reducing the harmful effects of the inflammation, there is a potential for a greater potential for repair and regeneration across the spinal cord, improving patient outcomes in the long term. Thank you.
Any questions? For anyone? No? Okay. Next presentation is by Mustafa Abdel Muttaleb. Yeah, these two. We're having some issues with sharing the wrong screen, so.
Hi, so I'm not Mustafa, but I will be presenting on his behalf, and I will be discussing our work on wirelessly controlling motor cortex activity using nanotechnology, specifically magnetoelectric nanoparticles. Wirelessly reading and writing to the brain has been a grand challenge for many years. However, a practical and durable system is yet to be created. Implantable electrodes are currently the gold standard, and new advancements such as ultrasound stimulation and optogenetics have come about. However, each of these methods have significant drawbacks, for example, the need for surgery with implantable electrodes and genetic modifications for that of optogenetics. In our research, we have made use of a new class of nanoparticles called magnetoelectric nanoparticles, which have unique properties, making them an excellent choice to activate specific regions in the brain with sub-millimeter resolution. We injected these particles into the rat motor cortex and were able to generate specific responses by changing the orientation of the magnetic field. This was achieved by moving the transducer location around the motor cortex. Now we'll look at some of our results. This graph shows the evoked responses over 60 trials for one of our experiments. We see that for the trials in blue, responses were only observed after we apply magnetic stimulation, and some residual responses do continue after we have ended that. Furthermore, after decreasing sedation, so that's in green, we see some random movement before stimulation, but significantly stronger responses with stimulation. Okay. Here we see that we can generate specific responses with higher frequencies by changing the orientation of the magnetic field. And this capability allows for selective stimulation of specific regions within the brain. Looking forward, this technology could be used to develop a non-invasive method for wireless brain-machine interface. And since these particles can be used to sense action potentials, this could be bidirectional. The ability to read and write to the brain would have groundbreaking applications in medicine, specifically when it comes to the treatment of neurological diseases like Parkinson's, as well as in brain augmentation and sensory and movement restoration. Thank you.
Very nice. Any questions? Oh, stop. Questions? Victoria, yeah, repeat the question, please.
So we actually don't have to do anything. They will naturally go through the system and be excreted out of the animal. And I'm actually not sure what concentration we put them into the brain. Do you know? 1 microgram. Yeah. Any other questions?
Should the hope to replace the class of technology that Kevin gave us?
Yes. Yes.
Also resolution, spatial resolution became much better. What we demonstrated right now was sub-millimeter resolution. Ideally, we can go to micrometers.
Yeah. You could use it with your stuff. Yes.
How long do the nanoparticles stick around if they're constantly being cleared? If you want constant stimulation long term, how often we can use them?
That's a really good point. I think we're still trying to figure that out. But yeah, no longer than a few days. So. Oh, okay, so let me go back. So I'm actually, like, it all depends on the movement of, oh, here we go, of this, you see the orange coils? So we move that, that's our electromagnet, and we move it in different ways. I don't know the exact orientation, but one way that it was facing, we get the like exhale movement, which is that, and then the other way we get finger movement. But I'm not exactly sure what direction it was pointing in. Yes? Perpendicular? Okay, one of them's perpendicular. Pardon?
Anisotropy. So it's like different direction or has like different effects.
Yeah, exactly. Anyone else?
Next presentation is by Aaron Stock, who is waiting impatiently behind me. So we have to stop the chair because for some reason there was an issue before. Oops. I'm sharing the wrong window. Okay, thank you. Hello everyone, I'm Aaron Stock. I'm a postdoc in Alicia Tomei's lab, and I'll tell you a little bit about our islet transplantation and encapsulation work. I was also a PhD student in our lab, so I've been working on this for a few years now. So, type 1 diabetes is a disease that's caused by your immune system on accident destroying some cells in the pancreas that are called beta cells that make insulin. You need insulin to regulate blood glucose, so if your immune cells destroy the cells that make insulin, you don't have it, so you can't regulate your blood glucose, so you have diabetes. So a way to cure this disease would be simply to replace these cells that are lost. You could do that with whole pancreas transplantation, but also with islet transplantation, which are the functional units in the pancreas. However, even if you do transplant new islets, you're still faced with the problem of the possibility of the immune system. You can see an evil T cell there trying to attack the transplanted islet. And so our strategy is to coat them in a layer of hydrogel that's based on polyethylene glycol. So that's supposed to serve as a physical barrier to block out the immune system. So the way that we've achieved these coatings traditionally was I tried to focus on the materials here. Is using a PEG malamide, and it's cross-linked with a PEG dithiol cross-linker. This cross-linking chemistry is very pH dependent, so at neutral pH it happens instantly. It's not practical. So we've had to lower the pH to like 3 in order to delay it sufficiently so that we can form these capsules around the islets. However, of course, using a very low pH, I don't know if you could see in this image, but we exposed islets to different pH levels, and naturally, as the pH became more acidic, the viability of the islets was decreased greatly. And so this acidic pH resulted in reduced cell viability, a low process throughput, and it was very difficult to perform for whoever was doing it. And so we came up with a new method which we were able to patent and license to a company that instead of cross-linking, by mixing the cross-linker directly, with the polymer, we would form the capsules still in the liquid state, and we used a cross-linking emulsion, which
It's based on the same cross-linking chemistry, but basically it could be accomplished at neutral pH. And so we were able to achieve the same conformal coatings on the islets with this method. And we noticed or observed improved cell viability because it was all neutral. We were able to improve our process throughput by 5 times, and it was actually very easy to perform and to train new people how to perform this. So that's it. Thank you.
Any questions? Yeah, question. Repeat the question.
Yeah, so there's a fluidic device basically. So you have like an oil phase running on the outside, and then within this flowing oil phase, we inject an aqueous phase coaxially on the inside. The aqueous phase is the liquid polymer with the islets of Langerhans resuspended in it. And basically, there's like 2 phenomena that occur. It's called there's a dripping to jetting phenomenon. So basically, yeah, that's how the capsules are created, and we have a device for that. But I didn't show that because I just wanted to talk about the material. Thank you.
And again, these are rapid-fire presentations, but I encourage you to discuss, after the presentation, after the session, we'll have some time to have more specific discussions. The next presentation is by Dr. Ashutosh Agavan.
No, stay. The hall's getting empty.
You got it?
All right, thanks. So I'm here representing my lab. Emma's already given a beautiful introduction on the philosophy. The idea is that most of the biomedical science is done using animals and graduate students. But we submit that the use of animals has limited applicability when you want to study diseases and specifically when you want to discover therapeutics. One of the diseases we got interested in early on was the metastatic disease related with breast cancer. The unfortunate part is a lot of women will get diagnosed with breast cancer in their lifetime, but it's not the primary tumor that kills them, it's actually a secondary metastatic process, and that secondary metastatic process is mediated by the primary breast cancer seeding a few cancer cells in the circulation, and at some point these few circulating tumor cells exiting the circulation and finding a home, let's say in a bone environment. And so the question became, can we isolate from the blood of a breast cancer patient these very few circulating tumor cells, and then release those circulating tumor cells from the surface that we captured on, and then build that patient's bone marrow on a chip so that we can recreate that entire process of a breast cancer cell flowing in the yellow chamber below, and noticing that there is a bone in the blue chamber above it, exiting the circulation of our chip, and going towards the bone and start causing metastases. So this has been work since I started at in fact, this was our first paper out the gate. And then over time, we've been building towards it, and the hope is to, if we can do it well enough, to not just discover new disease mechanisms behind breast cancer metastasis on a patient-specific basis, but without cutting into a patient, start isolating from a blood sample these circulating tumor cells and do patient-specific chemotherapeutic testing before we give it to the patient. Thank you.
Any questions?
You don't have a question?
I don't have a question. Thank you. Next presentation is by Courtney Dumont, Dr. Dumont.
Perfect, thank you. So, as Dr. Mon said, I'm Courtney Dumas, an assistant professor in biomedical engineering here. My lab interfaces a lot, as Giancarlo mentioned, with the Miami project specifically in the field of spinal cord repair. So today, I'm going to touch just very briefly on one of kind of the oldest projects we have in our lab. So spinal cord injury, it's going to be an injury specifically to the soft tissue that's within that bony spinal column there. So it's a really sensitive tissue, and when you have damage to it, you're going to have loss of your motor and sensory function below the injury site, as Giancarlo mentioned. What he didn't mention is that you actually have all these other important organ systems that are impacted following spinal cord injury. So a higher level injury is going to lead to not just an ability to do daily functions, but it could be an inability to use your urinary system or your lymphatic system, so your immune system. So it's a really important issue. What my team works with and bases all of our technologies off of is this base biomaterial. So we use a hydrogel tube, kind of like what Aaron was talking about with his PEG conformal coating. We also use a hydrogel microsphere, except we don't have cells in ours. So we take these little hydrogel microspheres and we fuse them together into these macroporous tubes. These macroporous tubes are this kind of foundational platform we work with. So on the side, you can see we have the spinal cord. It's a highly aligned tissue. So when there's a penetrating injury, which means there's a cut, you could have all these abnormal geometries. And our tubes allow us to conform to these wound geometries and pack the injury site and to support regeneration and tissue repair. So the image that popped up last is actually a tissue section from a mouse spinal cord injury. In the really dark region, that's where the injury is. So you can see it's a pretty robust injury model, and that it does not look like the nice continuous green section you see on the bottom. So our tubes actually support growth through it, and that's what the zoom is. It's kind of the supported growth through, which is nowhere near what we're needing to see functional recovery in humans. And so what we've been trying to work on since I came to Miami was to start integrating this with stem cell and gene therapies, and we've still only kind of gotten so far. So what Andrew Cicerello has been working on in my lab is the development of this new system, which is a biomaterial accumulating carriers for on-demand nanotargeting, or beacon system, for spinal cord repair. I'm feeling a little envious that I didn't use my name or his name. So essentially the idea is that we can have on-demand delivery that targets specifically to this implant. Existing systems have the issue of if we have a local depot, it's going to be depleted over time, and once it's in there, you can't pull it out and modify it on a patient-by-patient need. Whereas here what we're doing is we're loading our nanocarriers or our nanoparticles, injecting them intravenously, they traffic throughout your circulatory system, and then they bind to the receptors that we've embedded in our biomaterial, and they accumulate there where they then release their payload. And we can do this multiple times. So far we've done 40x dose, so we have a pretty extensive amount of drug that we could eventually deliver to this system, allowing us to have more tailorable drug delivery methods for spinal cord repair in the future. So, as I mentioned, Andrew Cicerello has really been the one driving this work, and hopefully we will be getting a paper submitted in the next week or two. And a lot of this has been in collaboration with Shanta Dyer's lab, who you guys met earlier, and she's been a really helpful asset on this project as well. Yeah, with that, I'd be happy to take questions. I saw Aaron's hand first. Great question. Yes, so So the question is, how do we do that secondary phase of annealing and get that structure, essentially? So our PEG hydrogels are cross-linked with a peptide, kind of similar to how you're cross-linking your method, right? So we have a specific peptide that uses the thiols to cross-link. And then we can pack it into, essentially we just use a mold, and the lumen of the tube is just a pin. So we do this all by hand. We've kind of given up on trying to use our bioprinter to do it because the mouse model is so small. It's kind of little below the threshold of 3D bioprinters for hydrogels. But we just UV crosslink as our secondary phase to anneal it into that shape. More recently, we've transitioned to a fully injectable system where we use the same, we use the cross-linking peptide, but then we use the thiol or the dithiol PEG to do a secondary phase of annealing. Yes? So we use PEG tubes. So the question was, why do we use polyethylene glycol tubes rather than a carbon nanotube? So the PEG tubes are much larger than a carbon nanotube. We also want something that is very similar to the mechanical properties of the spinal cord. And specifically, we have, through the hydrogel and the macroporosity of it, something that's very close approximation to the softness of the spinal cord, which is kind of like if you've ever made Jell-O and it's not fully set. That's pretty much what we're dealing with. It's not the most easily manipulated tissue. And over time, we want it to degrade and be replaced by the actual tissue that should be there. So, yeah. Ashu, I saw your hand.
So, like, it's a stupid question, but one of the challenges in cancer is when you cut the patient open, get the tumor out, then you hope that the tumor doesn't come back. But it seems to me if you can deposit some sort of a depot there that can attack chemotherapy 2 years later, then the micrometastases is coming back.
Yeah, I completely agree. So using a biomaterial where you can target it later for chemotherapeutics after you've excised the primary tumor, or even taking it a step further and integrating biosensors in there as well, or some sort of system where you can actually monitor if it's coming back, right? Then I think something like that has a lot of potential, especially since like the reoccurrence rates are relatively high in a lot of cancers. Yep. All right. Thank you all.
The next presenter unfortunately had some emergency, so couldn't make it. So the following presentation will be by Dr. Tigli. Oh, sorry. Wrong presentation, sorry.
Well, I found. I'll try to skip through all.
It's okay, you have time.
3 minutes.
Oh, yes.
Thank you. You do feel like a singer when you get this microphone. Anyways, you don't want to hear my voice. So Dr. Tigli, I'm with Electrical and Computer Engineering Department. So what I'm going to try to go real fast over a course of a research, or a course of like 20 years, I'll say, the beginning of that. But when Dr. Kizrev invited me to give the talk, he mentioned that there's materials and their applications. So I thought I should start with a material that I've been using a lot in my research for all these years. Quickly, what we do is, I'm a microchip designer, so anything we can put on a microchip, we do that. And I'm going to talk about 3 applications, so 3 minutes, 3 applications. And I have patented work in cancer diagnosis, liquid biopsy, biomarker detectors. And what you're seeing over there is our objective, actually. Well, that's an actual product of my research. It's a microchip on a nickel, right? It's a nickel. So our objective is to make things as small as that and also make them cost as low as that, right? So we are making headways with that, but not a nickel yet. So zinc oxide is a popular material that you might all recognize from ointments or sunscreens, right? So why is that a great material for our research is that it has amazing qualities, one of which is piezoelectricity, right? It's a great piezoelectric material, and also it's a semiconductor material. We know how to build it. So it's CMOS compatible. Why is that important? Because every one of you most probably are carrying a product, a CMOS product on you right now. You know, watches, your cell phones, your computers, and 98% of consumer electronics is CMOS. So we are trying to come up with biosensors that can be integrated with CMOS technology so that they can go into your cell phones, into your computers, wherever you want to put them, right? Anyhow, so zinc oxide, you need to characterize this material really well. You want well-oriented, uniform, high density, high quality, but most importantly, you want high electromechanical coupling. So we've been characterizing zinc oxide for many years now, and you see a good, high quality, well-oriented film over there. And why is that important? So the first application I want to talk about is the biosensor that I mentioned. We use principles of surface acoustic wave. So what is a surface acoustic wave? It's a reciprocal property, piezoelectricity is. So if you apply a voltage differential on one end, you're going to create a stress differential. And that stress differential is going to cause an acoustic wave that will propagate through to the output device, right? And at that end, it's symmetric. So mechanical stress differential is going to cause electrical charge differential, which will result in voltage difference. So this device you're looking at, surface acoustic wave, again, all of you have one of them on you because it's used as a filter in your cell phone devices. It's an electrical filter, right? So that's where you get your GSM signals, how you filter this out. So what we are using this, though, is if you, do I have my arrow here? Anyways. In the center, what we call the delay line, if you functionalize that region with any analyte of interest, you can actually detect that by applying at a very high precision signal, which will tell you whether you have that substance over there or not. So the second application that I want to quickly mention is in nanowires. So we also look at if we can build, again, zinc oxide, the same material, these beautiful nanowires, 1,000 of them is just one human hair strand, the diameter is. You can convert that nanowire into an actual transistor, which is, again, all of your CPUs operate on those tiny transistors. Now, if you functionalize the surface of that nanowire and, again, pass through a biomarker, a protein, what have you, and you capture that, you're going to cause an electrical shift, and again, this is an extremely sensitive sensor. So the beauty of this is it's a reproducible fabrication because we have been building these chips in semiconductor industry for the past 40 years. So we know how to do that. Although we have reached the end of Moore's law, is another topic. So the third one is we also thought that, okay, if we get the surface acoustic wave platform that we have, and integrate that with some acoustics, magnetics, and some electrical multi-physics environment, can we actually interact with cells, right? Specifically circulating tumor cells, like one of the talk mentioned, it's quite important to understand their properties. So by using the same principles, we built a system where we can get stiffness, elasticity, viscosity, all sorts of biophysical properties of cells, and be able to, you're seeing how our waves are interacting. That's a simulation. That's an actual cell. So finally, before going about, I see students, so they always come and ask me what kind of preparation are needed in this kind of research. So those are the courses that you can look into. I'm teaching one of them over there. I see some of my students from a bio-nano class, but you need to build up on those kind of knowledge before you can get into the research. Final note, that seems like the biggest logo University of Miami has, and I claim to have the smallest one. I don't know whether that's the case, but 100 micrometers, so we just do fun stuff like this. So. That's all. Is it 3 minutes or no? Questions? Yes?
Repeat the question.
Repeat the question. Okay. Say that again?
I have a good question regarding nanowire.
Yeah.
I saw that you basically create a platform in which you support, like simply support the nanowire from both ends. So that means we use the lateral properties of nanowire. But we know usually nanowires are 1D material and usually used for the longitudinal directional properties. So have you tried the longitudinal properties, or what was the motivation behind you?
For the nanowires that you have seen, they're not suspended. They're supported on both ends, but they are electrical contacts. So we are using purely electrical transistor properties. So we are not doing any electromechanical stuff there, unlike the surface acoustic wave. So you don't need suspension. All you need is making contacts on each end.
I see. So your electrical current goes from the one end to other end?
Yeah, the nanowire acts like, if you're familiar with FETs, field effect transistors, the nanowire acts like the channel of your transistor. So when you put any charge on it, it will modify the charge density, and it's going to cause a current change. Purely electrical, nothing mechanical going on over there. However, the same nanowires, there are other labs that are working on mechanical properties because they're piezoelectric, right? So you can make use of their piezoelectric properties like that, mechanical sensing purposes.
So with that, you just, I assume you just use the resistance change problem.
Resistance is part of it, but it's a more complicated scenario than that. Resistance is just part of it. So obviously it's current, so you have resistance, but there's capacitance involved in it, so it's more electrical engineering we can discuss offline. Okay? Any other questions? All right, thank you. Thank you, Dr. Muns.
Thank you. And of course, we kept the most exciting and the highest level of energy for the end. Dr. Chrysoff.
Yeah, thank you. Now I'm scared. You guys, I'll talk about cancer research also. You already heard so many talks today on cancer research, guys, using materials for cancer research. Each project is very important. Eventually, I'm sure cancer will be cured. We're still far from that, obviously. And each project is important, unique, and there are many angles. Each of them represents something special. So I will talk about joint collaborative project between Sylvester Cancer Research and engineering. So there are many people here. So we try to use functional materials. Functional materials, what means, you know, most materials to date have been focusing on one form of energy. It can be electric, magnetic, optical, thermal, acoustic, and so on, right? So recently, major breakthroughs in other industries, not in medicine, mostly semiconductor industry, what Dr. Tigli was talking about, actually have come because of functional, multifunctional materials where they finally learn how to use one form of energy to control another. That's a major thing. So it means you actually can take advantages of all the fields you can have while mitigating the disadvantages. You know, one thing cannot do it all. You know that. We all know that. That's why there are so many projects, right? And if we bring this multifunctional materials, sometimes we call them, that's why we call them intelligent, smart materials. It's a very new thing in medicine, for sure. And we want to be at that cutting edge, pioneer the stuff. So just to give you an example, of course, in 3 minutes, I can't talk about intelligent materials. It's a huge field. It's really coming up today. So just quick example. Cancer, you know. Cancer has also many angles to it. You know, biology is key. That's been our approach so far. There is also physics, chemistry, and to really address physics, we pretty much have to start from the beginning. For example, I'll tell you, look, the membrane potentials of cancer cells and normal cells have very different values. For example, for ovarian cancer, the difference is factor of 10. And we do not take advantage of it. You know what it means. Membrane potential defines the energy barrier you have to overcome to get inside the cell. You know, one of the biggest challenges in cancer is high specificity delivery. We want to be able to kill cancer cell at any level, at the earliest molecular level development, starting to be able to kill stem cells at the earliest stage when we barely see them, the diagnostic tools are not even capable of detecting them. We want to kill them right there. And to do that, we have to talk that type of language. And so this is exactly what we're trying to do. We're trying to use particles. In this case, you heard already about particles called magnetoelectric nanoparticles, where we can use magnetic fields to deliver energy to particles. And what these particles do, they convert this form of energy into electric fields. And electric fields tap exactly into this, for example, in this case, when I talked about membrane potential, into membrane potential. So what means we can provide the specificity we need. We can get inside the cancer cells. They can be stem cells, anything. Just we program particles so they target only the cells which have certain membrane potentials, while sparing all the surrounding cells. So it means we provide extreme, unprecedented level of specificity if we can do that. It's almost a dream goal, maybe a holy grail in treatment of cancer. We're far from doing this, but we definitely have some advances here, guys. Okay, let's see. This kind of little illustration. What you see here is an optical image, a fluorescent image showing cells, same type of cells here. It's a SCOF3, it's a ovarian cancer cells. And when, I wish I had that thing, the laser here to show. You see the right image, guys. The right image has lots of green cells. The fact you see them green, it means drugs got inside the cells. That's fluorescent. They are fluorescent drugs. They're conjugated with fluorescent agent, which allows us to see them under microscope. And the way we achieved that, we created particles which were tailored to that particular membrane potential of that cancer cells. And on the left, you see all kinds of other cells surrounding them. Just the fact we could get inside only there, that's the reason you actually see green color coming only from those cells. We definitely progressed in that field. You can imagine the amount of physics there. It's pure quantum mechanics, by the way, guys. Let me tell you. I'm definitely beyond the scope of this course, but it works. What can I tell you? It definitely works. We scanned, I would say, 10 different cell lines, ovarian cancer, breast cancer, and our main thing right now is glioblastoma, brain cancer, the biggest killer in cancer. We really want to get inside the brain, which we already do, and use this approach to destroy glioblastoma cells at all the stages. That pretty much summarizes my talk, guys. And we have millions of these slides. We always show them, guys. I don't want to bore you with this, but you got the main idea. This what we can see. These are metastasized cells. We catch them the same way. So it's a different way to target cancer cells with very high specificity, guys. I'm not going to bore you with this stuff, guys. That's all, guys. Thank you.
Question? Dr. Krizoev is doing magic with nanoparticles. I thought you were going to do magic with a microphone over there. But
Yeah, I know. This guy does magic. I just talk. Yep. Yes.
Yeah, so are these the same, first question is, are these the same nanoparticles that can read and write, right?
Yeah, absolutely.
So you mentioned that you're potentially using this as a therapy. Is there also, have you looked at potential for diagnostics? So for example, looking at like a TPM organoid and throw these particles.
Absolutely. Yes.
Because you said the membrane potential is different when it's normal versus cancerous. So are you able to use this to detect when it's becoming a more cancerous cell?
Absolutely. We did actually publish on this, yeah. I skipped this, but you got the idea. Obviously, there are many projects like this. You can grow from there. And that's actually indication it's a very fundamental work. Yeah, we've done it, and the way we did it is when we place particles in the cell media, right? Particles, because of their magnetoelectricity, mixing those two energies, they pick up electric energy from cells. The most standard way to look at the whole thing, we're all familiar with NMR spectra, nuclear magnetic resonance spectra. So nuclear magnetic resonance spectra easily pick up magnetic moment. They pick up magnetic moment from nuclear, but now we give them additional magnetic moment because of magnetic moment of particles, which are electromagnetic moments. It's even bigger. It's a major signal boost that we get there. Now, because cancer cells and normal cells have different electric signatures, and because electric energy is converted into magnetic, the spectra, NMR spectra, will contain that information. So you immediately, ideally, you can be able, NMR today is not really such a high sensitivity technique, but with these nanoparticles, you can make it extremely sensitive approach, yeah. This is one way to do it, by the way. There are millions of others, as you understand. Yeah. We don't have bandwidth to do it all. Absolutely, yeah. Yes. Yes.
You mentioned about the membrane potential. You tailored the nanoparticles based on the membrane potential. I just would like to know, that would be the straightforward question. We'd like to know what would be the uncertain level of the cancer membrane potential versus and the normal cells, because that might affect your...
Absolutely, yes, yeah. You know why I mentioned ovarian cancer? Ovarian cancer probably out of well-studied cancers has the biggest difference. Ovarian cancer membrane is about 5 millivolts, while normal ovarian cell membrane is 50 millivolts, 10 times. A big difference, right? Yeah. But look, I started with membrane potential because everybody knows that membrane potential. It's the most simplistic way to describe electric charges, right, in the two-phase media. Two-phase means there is intracellular and extracellular space. But in reality, it's always when you do it, life is much more complex. It's not just membrane potential. It's actually conductivity, dielectric permittivity, and it's actually much easier to control those two as well. But people understand membrane potential. That's why I always bring up membrane potential. You understand? So we've never even tapped into these resources. Resources are there. Yeah. So your question was what is the difference between cancer and that's what it is. Yeah.
The follow-up question would be my personal research. We produced this quantum dots.
Yeah.
I actually measured the beta potential of the.
All right. Okay. That's. Yeah. Oh, interesting, really. So you measured between normal and cancer cells, right? No.
My carbon dots.
Oh, okay.
I mean, my process is derived.
Okay.
I just observed that it might be an easy task to, change the potential.
Oh, yeah. No, but under equilibrium, by the way, most of the cancer cells, membrane potential is relatively straightforward to measure. And there are table values. There are lots of papers written on this. But you're right. It's not such a stable process, by the way. Those are the factors we always look at. You understand? Yeah, exactly. So definitely beyond the scope of this course. But it's a very good point. Yeah.
Thank you, Ron. Let's thank the speaker again. And again, I encourage you to contact the speakers if you have any specific questions, if you are interested in their work to learn more, to just contact them directly. And if you need contact information, just feel free to contact us and we'll connect with you. I think that ends the session.
Thank you, guys.
Please stay around for the poster awards.
Yes, if you want, stay around here, take a stretch, and we will reconvene in about 5 to 10 minutes.
Fabrice, thank you for moderating. Nice.
Sure. Thank you, Sirkin.
No sharing. No sharing anymore? Okay. Okay. So why we want to share? I think that you want to share something.
Yeah, we want to share it with the Zoom. We want to share with Zoom.
Zoom. It's a very hard task now.
I
You can
know.
close everything, or no? You need this one.
No, we don't need this.
You don't need this one. You don't. You need this one.
Only that to show there, and we want to share it.
It's not a view. Take care.
What do you want to do? I don't understand.
We want to share this
Over Zoom?
over Zoom. Yes, and then also on the screen.
I mean, then everyone can see it.
Yeah, but it's okay because we have no names yet.
Oh, what is no name?
We haven't clicked. When you click, the names come up.
Oh, okay.
I don't know why it's not showing. Our screen is not showing. Oh, because we don't have this open. We need to open the presentation.
No, it's open.
It's already open.
Maybe these, there's so much that...
You can close them all. But okay. Okay, ready. First, I think that you should select a slideshow and then share the screen. Huh?
Slideshow?
Yeah, the slideshow because it's show one by one. Oh, you're gonna see that?
Oh no, we don't want them to see the names
No.
No, they're not seeing it.
because it's an animation. This is an animation. You can show them.
Okay. You can do that.
Okay, don't.
So over Zoom.
Over Zoom.
Now we want to show it over.
Baba,
Navy.
Yeah, we can shoot it.
Yeah, one by one you can show it. Yes?
Yeah, and it's on the computer. To have it on Zoom over there.
You can also, sorry, please stand here and help.
Dr. Fuller. Yes. Which page is the thank you?
Oh no, okay, it's on the, we have to do this first. We gotta do this first.
And then thank you?
Yes, because the thank you's here.
Yeah.
You can't go because of the animation it'll show.
Yeah.
So why don't we just do the poster?
And then thank
and we'll you'll do thank you, I'll do thank you, and then we'll.
But so Renee is gonna start first?
Yes.
Okay,
Yes.
then you start because you wanna announce it and then I'll say thank you and then
Okay. We'd like to go ahead and get started with the poster awards. At this point, we'd like to hand it over to Renee Evans, who will announce the poster awardees.
Thank you. Okay, good afternoon, everyone. So for the category of undergraduate, do I just press the arrow? Yes. Okay. Nope.
This?
Back. Wait. Oh, there we go. Colette Thomas. Oh, okay. Okay, in the category of energy, environment, and manufacturing, Mark Ekin. Which one?
Thank you. Thank you so much. Renee. I really appreciate it.
Congratulations. You're welcome.
You can go over the...
That way. Or
Thank you.
all right, in the category of healthcare and biomedical. All right. Okay, in the category of materials, Alaric Zhang. All right, and the last category of machine learning and computer science. An Chen Sun. Is An Chen here? All right, is there someone who could collect his prize on his behalf? No? Okay. All right. All right. That's it. You take it? Okay. All right, perfect. All right. Thank you, everyone. Thank you to the judges. Back to you, Dr. Solo.
Hi everyone again. Thank you so much for attending this Research Day session today. This Research Day was organized by help of a lot of people. I'm going to have a thank you for all the persons who were leading this Research Day. First of all, I want to thank you, Dr. Sula Gabriello, for organizing the Research Day as a leadership of that. Then also all the judges that faculty members took the time and helped us all of evaluation of the posters. I really appreciate your time. And third, I'm gonna actually thank you for all GSE members that helped organizing this Research Day. They were taking time for the whole month, organizing, buying all the stuff that we needed. We can see all their names here, and also all the people who helped us for our purchasing, and all the facilities who were taking care of the catering and gave us this opportunity, this time to have our poster session in this auditorium and the other one. Thank you so much. And also by the way, Mohammed Qiyasi, I'm president of GSE. For those of you who has not informed about GSE, GSE is the Graduate Student Engineering Council. And we really appreciate each one of the graduate students who wants to be volunteer to be part of the GSE. We currently have some members from civil engineering, biomedical, electrical, but we still don't have members from mechanical engineering, also industrial engineering. So I'm asking for any of you who wants to be volunteer for the next events, they can participate and be a member of the GSE. And right now I just refer to Dr. Sala Gabriel for closing the session. Thank you.
Thank you. Yeah, so I wanted to also thank everyone, especially Alan and Alicia Sirkin, who provided the financial support to hold this, the dean, who facilitated all aspects of it. Wanted to thank Mohammed and the entire GESC for a wonderful poster session. The poster session was very exciting, and so thank you. A lot of work went into that. Greatly appreciated. Greatly appreciate the effort and the time of the session chairs and all of the speakers. Took a lot of time and effort to put that together, so thanks to everyone. And then the CoE staff, a lot of staff helped out. The names are listed here. And so the staff really came together to really assist us in getting this going. Lakeside Village staff, again, very much appreciated all the logistics. Wen Cruz, thank you so much for the video and the videography, and of course UMIT, who also assisted. At this point, I'd like to just say thank you, and the session is now officially closed.